Hello world! In this section, we will dive into the VGG net architecture through this comprehensive atlas. As you can see, we will discuss the VGG architecture through numerous aspects. First, we will go through the introduction and then philosophy of VGG. Then we will move on to the VGG architecture, discussing what the architecture looks like, the math behind convolution operation, design principles related to the VGG model architecture, comparison with peers, so some peers architectures, training VGG, VGG in transfer learning, how to implement transfer learning in VGG models, visualization and analytics, and variants and extensions, and also we will go through the legacy and impact, and then we will dive into the ecosystem of the VGG net architecture. So let's start and get started. First, we will discuss what is VGG net. Well, from pixels to perception, a layer by layer journey through convolution, pooling, and full connections. So we have a combination here. As you can see in the image, we have a combination of convolution layers, max pooling layers, and also we have fully connected layers. The convolution operation is the most fundamental operation within any CNN model. So a CNN model is short for convolutional neural networks, and convolutional networks is named after the operation convolution. So a CNN model must include at least one convolution layer. So we have a combination of convolution layers followed by ReLU layers, and then after the convolution layer we have max pooling layers. So this pattern is typically within most of the CNN layers. After a set of convolution layers we have one max pooling layer, and then at the last or at the end of the architecture we have fully connected layers to train the model how to classify into a predefined amount of classes. Okay, so as you can see, we have an input image. The height of the image is 224 and the width is 224. Why we choose 224? Well, because this is a common size in computer vision. It's a common practice to resize your images into 2 to 4 by 2 to 4. And then we input this image into the first convolution layer. The convolution layer will apply a number of kernels or an amount of filters on the image to try and detect the features, to try and extract the patterns and features. So we are trying to teach the model what this image contains. Then we have another convolution layer which detects more complex, more fine-grained patterns. After these two convolution layers we have a max pooling layer. The max pooling layer will reduce, as you can see, it reduces the dimensionality of the image. So now we have 112 by 112 by 128 number of kernels. Okay, so here we have a max pooling layer to reduce the dimensionality of the image. So it helps reduce the dimensionality, and thus it reduces the number of parameters in the model, making the model faster for computing on the image. Okay, so we are reducing or downsizing the amount of parameters in order to make the model faster to compute and also to proceed computations on the image. After this max pooling layer, we pass it to another convolution layer. This convolution layer will receive the same height and width that is outputted from the max pooling and apply a different set of filters, a different set of kernels to try and detect more features. Now you might ask, what is a feature? Well, a feature could be anything. we don't define what the model learns. This is the whole magic of machine learning. The whole magic of machine learning is that we don't instruct what the model learns, because artificial intelligence is getting some inputs and getting the right outputs and then passing them or feeding them to a model, and the model figures out what the model should learn, and then it figures out the right set of instructions, and then it uses these instructions for later on to make predictions in inference mode. While if we want to discuss the programming in traditional way, we have inputs and we have instructions, and we apply the instructions on the inputs and then get the outputs. But here the model will learn by itself, the ability to learn by itself. So we are teaching the model to learn useful features from the image. If you wanna discuss the what features are, features could be anything. Could be edges, could be the angles, could be lines, stripes, or the color gradients, the brightness of the image, the contrast of the image, the saturation of the colors in the pixels. So we have a massive amount of features that the model can learn. Then we pass it to another convolution layer. Then we downsize it further using another max pooling layer, as you can see. Then we have instead of having just 2 convolution layers, we have 3 conv layers, as you can see. So we have convolution followed by another convolution followed by another convolution, and of course the blue layers here are composed of convolution plus ReLU, and the ReLU layer is short for rectified linear unit. The rectified linear unit is a layer that enables the model to learn complex nonlinear relationships. So it allows the model to learn complex curves, to learn complex patterns in the image. Then we pass it, as you can see, to another max pooling layer and the same pattern. So we have convolution, 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 max pooling. Then we have the final set of convolutions, 3 conv layers, and then the last max pooling. And this max pooling layer passes the image to a fully connected layer, and the fully connected layer is the same as the linear layer. So we have 2 terms in for a fully connected layer. You can name it fully connected, and also you can refer to it as a linear layer. So you can refer it as a linear layer or a dense layer. Okay, and then we have another fully connected layer, and then this is the last fully connected layer. And of course, as you know, we have the authors of the VGG trained their model on the ImageNet, so they have 1000 neurons to classify into 1000 different classes. Okay, so we have 1000 neurons to classify to 1000 different classes and objects. Here we have a simple philosophy, guiding philosophy about the VGG. VGG isn't just a deeper net, it's a deeper philosophy, proving that simplicity and uniformity, when extended with depth, can transform perception into cognition. In the ever-evolving landscape of deep learning architectures, the VGG network occupies a seminal place, not merely as a performance model, but as a philosophical statement or on architectural design. At its core, VGG embodies the belief that elegant simplicity, when methodically scaled, can yield extraordinary expressive power. And as we said, we have 3 important pillars that VGG stand on. So we have the first pillar, simplicity. So it is considered a simple model. As you can see, it's just a set of convolution layers followed by max pooling layers followed by fully connected layers. So it's considered a simple model. And also the depth. At that time, this architecture was one of the most depth models at that time when they launched this architecture. So it was a deep model. And also the third pillar is uniformity, and as you know, this architecture applies the uniformity principles, where it has this pattern of convolution, convolution, max pooling, conv, max pooling, and then we have 3 conv layers followed by a max pool layer. Okay, so this is a general principle about the VGG net architecture. And then we have chapter concepts. So let's now talk briefly about the origins of VGG. ImageNet ILSVRC 2014. 2014 was the year the VGG was unveiled to the world, competing in the ImageNet large-scale visual recognition challenge. So ILSVRC is a challenge, and it is short for ImageNet. So the I stands for ImageNet. ImageNet is a large-scale database of images. Large, and then L is large, S scale, and then V visual, R recognition, C challenge. VGG models ranked among the top in classification and also localization. Shift from handcrafted to deep learned features. So the VGG model marked a transition from feature engineering like CIFT, HOG, to feature learning through deep networks. And also it came from the Oxford's Visual Geometry Group contributions. The author Karen Seminian and Andrew Zisserman from the VGG group introduced this model, emphasizing architectural simplicity through depth. The VGG architecture, as we discussed, we have an input image, fixed size, 2 to 4 by 2 to 4, and note this is the height of the image, and this is the width of the image. Okay, so we have a 2 to 4 by 2 to 4, the height and the width are of type RGB, so red, green, blue. So the number of color channels of these images are 3 color channels: height, red, green, and blue image. Standardized pre-processing by subtracting the mean RGB value. So they have standardized their images through a pre-processing by subtracting the mean RGB value. Then we have conv layer. All use 3 by 3 filters, which is applying the uniformity principle. They are using the same kernel size across the whole architecture. So all use 3 by 3 filters. And if you don't know what a filter is a small matrix, a small window that's convolved over the image to extract features, to learn the patterns. With stride of 1, so they used stride 1 and padding as 1 to preserve spatial dimensions. And the spatial dimensions are the positions in the image where the model, the convolution layers, tries to learn the spatial features. So where this object is located, at the top of the image, or at the center of the image, at the bottom of the image. So it learns some spatial dimensions. It learns the spatial content of the image. And then we have ReLU activations throughout. After each convolution layer, we have a ReLU layer. As we said, ReLU is short for rectified linear unit, and it is a activation function that helps the model learn complex nonlinear correlations. It helps the model learn complex nonlinear relationships after every convolution, enabling nonlinearity and faster training. And also it helps to make the training faster. Then after a set of convolution plus ReLU layers, we have max pool layer. The max pool layer has a kernel size of 2 by 2, so its window size is 2 by 2, 2 rows by 2 columns after certain conv stacks, and the role of it is it reduces spatial resolution by half. So it halves the image, reduces spatial resolution by half, helping in abstraction and computation efficiency. And there's a saying in AI that intelligence is abstraction. So this is a trend across all deep learning field. We always try to take the abstraction of the data to make the data more abstract and also still representative about the image. Okay, so we can compress the image into a compressed version that's also yet still representative about the image. And then fully connected, we have 3 dense layers, 2 with 4096 units, followed by a finally 1000 unit layer for classification over ImageNet classes, as we discussed earlier. And then we have diagrams, VGG 16. We have variants of the architecture. We have one variant that is VGG 16, and we have another variant or another type that is VGG 19. So VGG 16 contains 13 convolution layers plus 3 fully connected layers. So we have one type of VGG architectures that is called VGG 16, contains 13 convolution layers plus 3 fully connected layers. And VGG 19 contains 16 convolution layers plus 3 fully connected layers. Blockwise illustrations showing progressive depth and feature abstraction. Now let's move into the mathematical formulation of convolution. So the 2D convolution operation for a single output channel can be expressed as the following equation. So here we have an equation y of I comma j equals the sum, and then here the sum is over the m starts at 0 and then until m minus 1, and here we have the sum n starts at 0 until n minus 1. Then we have the x, which is x here, as you can see, input image or feature map. So it could be the input image or feature map. And if you don't know what a feature map is, the feature map is the output of the convolution layer. So the convolution layer produces the output. This output, we refer to it as feature map, and it is the map that contains the features, the extracted features, the patterns that the convolution has learned. And then we multiply it by the kernel, and k refers to the convolution kernel or filter. So you can say filter or kernel. It means the same thing. And as we said, the filter is a small window that's convolved over the image or that moves across the image to extract the features. It goes from the left to the right and from top to bottom, trying to teach the model what this image contains, what this image emphasizes. And then we have this m times n, which is size of the kernel, for example 3 by 3. So the size of the kernel is an important hyperparameter, and you have to choose it. As you as a machine learning engineer, you have to choose what the kernel size is. You can define it as 3 by 3 or 5 by 5, or you can make it 7 by 7. You can try different hyperparameters or different values for the kernel size and see which one performs the best. Okay, so the size of the kernel is an important hyperparameter. What about the content of the kernel? The content of the kernel are numerical values, and these numerical values, the backpropagation algorithm and also the gradient descent algorithm will try to optimize them. So you don't define what are the weights. You don't define what this kernel contains. The model itself defines what should this kernel contain. It starts with random values. So the kernels, the filters, the windows starts with random values. It initializes them as random values, and then when we train the model using the backpropagation algorithm and also the gradient descent algorithm, it optimizes, fine-tunes, modifies, alters these weights, these numbers to better represent our data. And also another name for the kernel is a feature detector. Now let's move into the design principles. So why 3 by 3 kernels? VGG exclusively uses 3 by 3 convolutional filters, the smallest size that still, so this is the smallest size that still captures directional information from left to right, top to bottom, and also moving across the center. Stacking multiple 3 by 3 layers, so 3 by 3 convolution layers, increases the effective receptive field. The receptive field is the region that the kernel covers. So the region that the kernel covers is called as a receptive field. Important terminology in CNNs. For example, 3 by 3 layers approximate a 7 by 7 field, while introducing more non-linearities and reducing the number of parameters compared to larger kernels. So a 3x3 kernel, while introducing more non-linearities and reducing the number of parameters compared to larger kernels. Okay, uniform depth per block. VGG maintains consistent design within each block. Each block contains either 2 or 3 convolution layers of the same depth, followed by a max pooling layer. This modular structure not only simplifies implementation but also enhances interpretability and scalability of the architecture. So uniformity, uniform depth per block. And then we have here, if you move down, no LRN, which is local response normalization, unlike AlexNet, which introduced LRN, local response normalization, to mimic lateral inhibition seen in biological neurons. VGG emits LRN. Experimental results showed that LRN didn't improve performance on ImageNet while increasing computational complexity, making it unnecessary in the VGG design. So this is an important distinction. And then deeper models generalize better. A key insight from the VGG paper is that depth. So they emphasized depth. They truly emphasized depth. So they realized that the more depth the model, the more ability that the model is able to find patterns and also to generalize well to new unseen data. A key insight from the VGG paper is that depth improves representational power. Deeper networks can learn from abstract and hierarchical features, allowing them to generalize better across various datasets and tasks. VGG's 16 and 19 layer configurations significantly outperformed shallower models like AlexNet. And now we have a comparison with peers. We have here the model, and then key, trials, and then the number of parameters. So here we have AlexNet. AlexNet is a CNN model consisted of 5 convolutional layers. So just 5 convolutional layers. And then 3 fully connected layers. So these 5 convolutional layers are followed by 3 fully connected layers. It uses large 11 by 11 filters. So they used large kernels, 11 by 11 filters in the first layer. Employs local response normalization, which we discussed earlier, and ReLU activation. And the number of parameters here, really important, they have about 60 million parameters. And the top 5 error is 16.4%. Then we have VGG 16. VGG 16 consisted of 13 convolutional layers. So they had 13 convolutional layers, so more conv layers compared to AlexNet, with uniform 3x3 filters. So they applied uniformity. They used fixed kernel size across all the conv layers, 3x3 filters. Simple and deep architecture. They have a deeper architecture compared to AlexNet. And then ReLU activation, they used ReLU activation, no LRN, which is local response normalization, and heavy reliance on depth. Okay, so here they had 138 million parameters. The top 5 error is less than AlexNet. They had 7.5%. And then GoogleNet utilizes inception modules combining multiple filter sizes, 1x1, 3x3, 5x5. So they had a varying number or varying sizes of the kernels, 1x1, 3x3, and then 5x5. Deeper and wider. Of course, GoogleNet is deeper than VGG, deeper and wider, aggressively optimized for fewer parameters. They only used about 6.7 million parameters, so less than AlexNet and less than VGG 16. So they had a pretty efficient model, aggressively optimized for fewer parameters. And the top 5 error is 6.7%. Then we have ResNet 50 with 50 layers deep, introduces residual, which is skip connections to mitigate vanishing gradients. Batch normalization also, they applied batch normalization after every convolution. It has about 25 million parameters, and the top 5 error is 5.5% accuracy, or top 5 error. Now, if you go down here, AlexNet versus VGG. Well, VGG uses smaller filters compared to AlexNet, but many more layers. So we have many more layers in VGG. This yields final hierarchical feature extraction. So this yields final hierarchical feature extraction. Feature extraction is the process of extracting features, patterns from images, from data, at the cost of more parameters and compute. VGG versus GoogleNet. While VGG favors depth and uniformity, GoogleNet aims for efficiency through parallel. So GoogleNet aims for efficiency through parallel convolutions and reduced parameter count. As we said, GoogleNet is distincted for its reduced parameter count. GoogleNet has just 6.7 million parameters. Then VGG versus ResNet. VGG showed that deeper is better. ResNet took it further by enabling extremely deep networks, so 50 plus layers, through skip connections, reducing training issues. So when the architecture goes deeper, it suffers from the vanishing gradient problem, which is the gradients becoming too small and useless. So they have solved this issue via using the skip connections, the residual connections in ResNet. So VGG served as the bridge between early deep learning models like AlexNet and modern ultra deep architectures like ResNet, making it a foundational reference point in the evolution of convolutional networks. Training VGG. So here we have some aspects about training VGGs. Training the VGG network represents a disciplined application of deep learning optimization principles, emphasizing both rigor and simplicity. Its training regime or regimen is structured to maximize convergence, stability, generalization, and reproducibility across large-scale datasets like ImageNet. So the loss function is cross entropy. So the cross entropy is the loss function for classification problems. We have two different types of problems in machine learning. We have regression problems, and we have classification problems. For classification, we use cross entropy loss, the cross entropy loss. And for regression, we use other loss functions like mean absolute error, mean squared error, and so on. So the cross entropy loss is employed as the objective function. The objective function is an important concept in machine learning. So the model tries to decrease the objective function. So we have an objective function, which is in this case loss function, cross entropy loss, and the model tries to reduce this loss, tries to decrease the loss function, to decrease the objective function. When the loss goes down, the accuracy goes up, goes higher, and then we have more accurate classifications or predictions appropriate for multi-class classification. So the cross entropy appropriate for multi-class classification, and inside classification problems we have three types of classification. We have multi-label classification, multi-class classification, and we have binary classification. So binary classification, where you have a model that classifies into two different classes. For example, if you want to train a model to classify whether this image contains a certain type of animals or the other. For example, if you want to train a model to recognize lions from tigers and so on. So if you want to classify into two different classes. So we use binary cross entropy. And multi-class classification, we use cross entropy to compute the loss between the predicted or the classified versus the truth, the ground truth. It integrates the softmax activation and negative log likelihood, penalizing confident but incorrect predictions. So the cross entropy loss penalizes confident but incorrect predictions. When the model predict, for example, we are classifying whether this image is a cupcake, contains cupcakes or not. When this image doesn't contain cupcakes, where in fact it contains cupcakes, then the model predict that no, it doesn't contain cupcake. For example, the model classified it as chocolate cake. Then and also the confidence rate is high. So the confidence rate, for example, is 90%. So then the cross entropy loss function will penalize the model for the confident but incorrect predictions. This loss effectively guides the network to produce probabilistic outputs. So this cross entropy loss function effectively guides the neural network to produce probabilistic outputs aligned with the target class distributions. Then we have optimization strategy. Which strategy do we use for optimization? SGD with momentum. SGD is short for stochastic gradient descent. Stochastic gradient descent with momentum. The network is optimized using stochastic gradient descent, SGD, augmented with a momentum term of 0.9. This momentum helps the optimizer traverse flat or oscillatory regions of the loss landscape more effectively, accelerating convergence and avoiding local minima. The loss landscape is the surface of the loss function. It looks like a surface that goes up and down of the loss. Here we have optimization strategy as SGD. The loss function tries to compute how wrong our model is. So how wrong is your model? And the optimizer, based on the loss function, will update the weights, will try to fine-tune the weights to better represent our data. So the optimizer will update our weights, will fine-tune the weights, will alter, change, modify the weights, and the loss function will compute how far the model's classifications compared to the ground truth. So here we have a probabilistic model that produces probabilities. So how far the probability distribution, the real probability distribution from the predicted probability distribution. And we also mentioned that the softmax function, the softmax is an activation function that we use at the final layer, at the very final layer here, the fully connected layer. It contains a softmax function. So why do we use softmax? Because softmax maps the raw scores, the raw logits into probabilities that we can choose the index of the highest probability, and this will be the predicted class. So the softmax function, okay, we use it as an activation function for the last layer, for the last final layer, to map logits into probabilities, to normalize the logits and turn them into probabilities. Then we have the batch size. The batch size is a really important aspect or concept in machine learning. What is the batch size? Well, if you have a large training dataset, for example, containing 100,000 images, then it's not reasonable to train your model on all of these images in one hit at one time. So we batchify our dataset. We turn it into batches, into small batches that the model will handle one batch at a time. So the model will be faster, and then also your memory can fit the batch within it. Because if you have 100,000 images, then typically your memory wouldn't fit that that much data. So you have to batchify your dataset. And a batch size of 256 allows the model to leverage GPU parallelism while maintaining gradient estimation stability. So the gradient estimation stability is how much stable your gradient estimations. It offers a balance between stochasticity, helpful for generalization, and computational efficiency. Because when you have a whole 100,000 images dataset, then your model, if the model is able to compute on them, let's say you have a fairly large memory and you have a really good computations properties. For example, you have fast GPUs and you have a large capacity of the memory, then your model will be able to compute on this large dataset, but you have to know that the model will update the weights after it sees all 100,000 images. So the model will not update its internal weights until it has seen all of these images. But batches helps us to make quick updates to the weights. After each set number of batches, after each batch, the model will update its internal weights. So the model will update its weights, its patterns, its coefficients after each batch. So the updates will be quicker. Okay, so this is the purpose of batchifying your data. So they used a batch size of 256, which allows the model to leverage GPU parallelism while maintaining gradient estimation stability. It offers a balance between stochasticity, helpful for generalization, and computational efficiency. And stochasticity, because SGD will choose randomly will choose elements, will choose images to update the weights. So it is stochastic. Then we have regularization. Regularization dropout in fully connected layers. So the dropout layer is a really important layer that helps reduce the risk of overfitting. So if your model is suffering from overfitting, you can apply a dropout layer to reduce the overfitting problem. To mitigate overfitting, given the large number of parameters, dropout is applied in the first two fully connected layers, typically at 0.5 probability. So 50% of the neurons will be dropped out. 50% of the neurons will be disabled, deactivated. This randomly deactivates neurons during training, encouraging redundancy and robustness in learned representations. So in machine learning, our goal is to build less dependent models. Our goal is to build less reliant models that are less reliant on specific properties of the data, models that are less reliant on specific features and patterns inside images. So when we train a model, for example, on images that classify pizza and steak, we want to make the model less reliant on noise, on noisy patterns, noisy pixels. For example, the spoon or the color of the plate or the color of the table. Okay, so we want to make the model less reliant, less dependent on specific patterns, on specific features. So we want the model to learn robust, fine-grained, generalizable features, generalizable patterns. Okay, and dropout also helps us with this concept. It makes the model less reliant on specific neurons, helps the model becomes less dependent on specific neurons and specific units inside the architecture, and to be more robust, more generalizable patterns. Then they used also data augmentation. Data augmentation are techniques inside machine learning and deep learning that helps you create or generate more data or more training samples, like flipping, applying some geometrical applications like flipping, also like, for example, rotating, and also applying some photometric. So we have two types of data augmentation. We have geometric augmentations and we have photometric augmentations. The geometric augmentations like flipping, rotating, cropping, And also we have photometric augmentations, like changing the brightness of the image, changing the contrast, the hue, the saturation of the image, okay? And then we have scale jitter. Scale jitter, this is the class inside PyTorch that helps you manipulate the brightness, the contrast, the saturation, the hue of the image. It's called a scale jitter. Then, or we have another class that's called color jitter. We have another class that's called color jitter that manipulates the brightness, contrast, hue. But scale jitter helps us manipulate the scaling of the image. Okay, but it has the name jitter. Then we have RGB shift, so we can shift the RGB channels, which is red, green, blue. As we said, when we convert images into tensors, into arrays, they are converted into 3 channels: RGB, red, green, blue channels. VGG employs extensive data augmentation to increase training diversity. So we can go into the data augmentation atlas, which is not inside Knowledge Hub, and then we have data augmentation. Here we have a comprehensive list of data augmentation, as you can see, a comprehensive atlas of data augmentation techniques. There are numerous types of data augmentations. We have image data augmentation. We have basic transformations like flipping horizontally or vertically. So we have horizontal flipping, vertical flipping. We have rotation, cropping, scaling and zooming, translation, shifting, brightness, changing the brightness, contrast, adjustment, shearing, and also we have color jitter, which I talked before. And we have advanced techniques like cut out or mix up, cut mix. These augmentations are based on papers. Also, we have text data augmentation. If you deal with natural language processing, you can also augment the text. For example, synonym replacement. So you can replace a word with its synonym. And we have random insertion, deletion, random swap. We have back translation, noise injection, for example, spelling mistakes, and these kind of things. And also we have here audio data augmentation techniques. For example, time shifting, pitch shifting, speech tuning, and so on. Then we have here use cases in deep learning. So we can use the data augmentation techniques in computer vision. So computer vision deals with the domain of images, image classification, object detection, segmentation, and the augmentation examples like flipping, rotation, mix up. So we have numerous types of augmentations that you can read through here. Now let's get back. As we said, we have data augmentation, we have flip, scale jitter, which changes the scaling of our image, and we have RGB, red, green, blue shift. VGG employs extensive data augmentation to increase training diversity. So as we said, data augmentation is a technique in deep learning that helps us create more diverse images, or to diversify our dataset. We have horizontal flipping, introduces invariance to lateral orientation. So when you flip your images the other way, for example, when you make horizontal flipping, then you teach your model you teach your model to be less dependent on the direction of the object. For example, if you are training a model on images of lions and tigers, then when you flip the image of a tiger and you teach the model on the flipped image and also the original image, then your model will become aware of the tiger object whichever direction it was directed towards. So with whatever direction your tiger is heading towards, the model will be able to detect that this is a tiger. Then we have scale jittering. Randomly resizes, as we said, scale jitter, randomly resizes the input within a scale range, for example, 256 to 512 before cropping, helping the model generalize across object sizes. And also we have RGB color shift, adjusts color channels to reduce reliance on absolute color values. So RGB, red, green, blue, the system of the colors. We have RGB color shift data augmentation technique, which adjusts color channels to reduce reliance on absolute color values. Then we have here training schedule, about 74 epochs. So they trained their model about 74 epochs. The training typically spans 74 epochs, or 370,000 mini batches iterations. So they had 370,000 mini batch iterations. The learning rate starts at 0.01. So the learning rate starts at 0.01 and is manually reduced upon plateauing of validation accuracy, adhering to a stepwise decay strategy. So they used a learning rate scheduler. The learning rate scheduler helps you schedule your learning rate. We have two types of setting the learning rate. We have a fixed learning rate, which begins as a number that you choose and then continues across the whole epochs. Across all epochs, your learning rate will be the same, will be fixed. For example, if you set it as 0.001, then it will train your model for all epochs on this same learning rate. This is called a fixed learning rate. Whereas they applied a learning rate scheduler, which helps you schedule and manipulate your learning rate across epochs. So the learning rate starts at 0.01 and is manually reduced because your model first starts with crazy weights, with crazy patterns. It has to learn. So we have to make the learning rate high. Then over time, when the model now, by reaching the epoch, for example, epoch 30, the model has learned useful patterns. Now it doesn't need that much training. So we need to manually reduce upon plateauing of validation accuracy. When the validation accuracy loss curve or the validation accuracy curve plateaus, adhering to a stepwise decay strategy. The success of VGG's training pipeline underscores the power of disciplined architectural choices and optimization practices, reaffirming that depth, regularization, and augmentation can achieve state-of-the-art performance even without architectural novelty. So we infer that the success of VGG's training pipeline underscores the power of disciplined architectural choices. So the architectural choices, for example, the learning rate, the number of layers, the number of filters, and optimization practices, reaffirming that depth, regularization, like dropout, and augmentation, like flipping, rotating, can achieve state-of-the-art performance even without architectural novelty. So the state-of-the-art, if you don't know, it means best in business. So state-of-the-art is another word for best in business. VGG in transfer learning. Modes of use. VGG's structured and deep feature hierarchy makes it ideal for transfer learning. It can be applied in two primary ways. First, fixed feature extractor. So we have two types in transfer learning, or precisely we have three types of transfer learning. We have the first type, which is called as is transfer learning, or also called the original model, where you bring the model without any changes. You just bring the model with the same weights they have reached and then use it for your own specific task to classify or to predict. Whereas we have also the second type of transfer learning as feature extraction, which is really common. Feature extraction, you take the model, is where you take a model and then freeze the base layers. So you make the base layers frozen. The base layers are the layers that extract features. If you go up here, these are called feature extractors. So these layers here all are called feature extractors. Okay, so all of these layers are feature extractors. And then these layers here, the fully connected ones, are called the classifier head. So it classifies. So when you do feature extraction, you freeze all convolution layers. You must freeze all convolution layers, but keep the fully connected trainable. This is called feature extraction. Whereas the first type, as is transfer learning, you keep all of the layers, including the fully connected, frozen. And then you use the model, the model's weights, the pre-learned weights, the pre-trained weights, you use them and leverage them for your own task, for your own use case. But the second type, feature extraction, freeze all of the base layers, freeze the feature extractor layers, and then it trains the classifier head. This is called the classifier head. Why? To suit your own problem. Because when you take the model, for example VGG or ResNet or any model that is trained on ImageNet, and take it to leverage it on your own problem, on your own task, you might use another set of classes. So you might have different classes. You might classify into 10 different classes. For example, car, trucks, ships, airplanes. So you might have a different set of objects, a different set of classes, other than the ones that exist inside ImageNet. So you must train the fully connected layers. This is called feature extraction. Okay, feature extraction. Here we have in the transfer learning, fixed feature extractor, freeze all convolution layers. So we must freeze all convolution layers and only train the classifier head. This is effective when the target dataset is small. This is effective when the target dataset is small. This is a really, really important and significant note. So we typically use the second type, which is feature extraction, when we have a small training dataset. So if you have a small, when you want to do transfer learning and you have small training dataset, then you get to use feature extraction. You have to use feature extraction, where you freeze all convolution layers and only train the classifier head. This will be effective when the target dataset is small. And then we have the third type of transfer learning, the last type of transfer learning, which is fine-tuning. Fine-tuning is the process of unfreezing some top layers and retrain them on the new dataset to adapt the learned features more closely. So the third type of transfer learning is called fine-tuning. Fine-tuning, you unfreeze some of these layers, some of these feature extractor layers, you unfreeze them alongside with the fully connected ones. Okay, so this plus the feature extractor model, the feature extractor layers, and then you retrain them on your own specific dataset. This type is preferred when you have a fairly large dataset, when you have a fairly large training dataset. Okay, so we have three types of transfer learning. As is transfer learning, where you leverage a model as it is, the weights as they are, you don't change it, you take it and use it in your own task, and this is rare. Secondly, we have feature extraction, where you keep all of the base layers the same, you freeze them, you make them unadjustable, unmodifiable, and then you just retrain the fully connected ones. Why? To adapt the new model with your own specific datasets. You don't have 1,000 classes like in ImageNet. You have 4 classes, for example, 10 classes, and they are different from ImageNet. So you have to retrain the fully connected to adapt to the new dataset. The third type is fine-tuning, where you will unfreeze some of these layers to retrain them on your specific features, on your specific patterns. Then the model will be able to classify or predict on your own dataset. Versatile applications. Well, VGG has been successfully applied across a wide range of domains: medical imaging, classifying chest x-rays, CT scans, and pathology slides. We have agricultural diagnosis, agricultural diagnosis, detecting plant diseases from leaf images. And we have art and style transfer, extracting multi-level visual features for style blending. And we have here a sample code that will help you get a pre-trained model VGG from PyTorch using the PyTorch library. So from torchvision import models. The models package contains, if you search here, torchvision models. Well, if you go to torchvision, then we have here torchvision package, and then we have here the docs. If you go to PyTorch domains, we have a numerous amount of domains. So we have torch audio, torch tune, torch vision, torch rec for recommendation engine. Now we want to go to torch vision, and then if you go to models, we have models and pre-trained weights. Here we have a long list of classification models. So if you go down here, we have classification, we have AlexNet, ConvNext, DenseNet, EfficientNet, and also we have this VGG. So we can import this VGG model from the PyTorch. The VGG model is based on this paper, Very Deep Convolution. So this is the paper by Karen Siminian and Andrew Zisserman. Very Deep Convolution Networks for Large-Scale Image Recognition, submitted on 4 September the 4th, 2014, and last revised 10 April 2015. Okay. And then import torch.nn as nn. Torch.nn is a package that contains the most important building blocks for NeoTalks, for neural networks. And then you initialize the model by going model equals models, the models package or the models library .vgg16. You access the VGG16 architecture. So we are now choosing the VGG16 model, not VGG19, and then setting the pre-trained equals true. Then we have freeze feature extractor. So we want to freeze the feature as I told you. Now we are taking the weights of the feature extractor and freezing them. So we have to freeze them in order to do feature extraction in transfer learning. So here we are freezing the weights of all these layers, conv layers, max pool layers, and all of these. Max pool doesn't have weights. Okay. So here, if you see 4 parameter, so for each parameter in model.features.parameters, model.features access the features layers, and then .parameters, then param.requires grad. So we are setting the requires gradient. This is an important attribute in PyTorch. Requires grad. Requires grad is an attribute or property inside each of the layers in PyTorch that will set whether this layer is trainable or not. So does this set of parameters requires gradient? Well, false. So we are freeze feature extractor. So now we are freezing the layers, the feature extractor layers, to keep the weights the same, to preserve the weights, to protect the weights, by constructing a for loop for parameter in model.features. Features attribute will access the features here. If you go up, these are called feature extractor layers. Conv, max pool, conv. These are all called feature extractor layers. Okay, and these are called classifier heads or classification head. Okay, really important if you want to do transfer learning. This is the art of transfer learning. Then we are setting the parameter or the property requires gradient as false to freeze them, to make them untrainable, non-trainable. Then replace the classifier head with the number of classes that you have. Here we have, for example, 4 classes in this course. We have 4 classes. We are classifying it to 4 classes, so we can set it to 4. Here we have model.classifier at index 6 equals nn.linear. So we are changing the linear layer The linear layer is the fully connected layer that will classify, and it receives 4096 units or inputs, and then it produces 4 logits, 4 probabilities. So we are now changing or adapting the classifier head into our own use case. This is the art of transfer learning. How do you take pre-trained models and then adjust them for your own task by freezing the feature extractor layers and then replacing the classifier head? The benefits reduces training time. So one of the most important benefits of transfer learning is that you reduce the training time. So here, this is really important. Transfer learning helps us retrain pre-trained models with less training time. Why? Because they are powerful already. These models are already powerful. They are trained on ImageNet. They understand edges, they understand borders of the objects, boundaries, they understand the texture, the shapes, the triangle shapes, square shapes, pyramid shapes, rectangle shapes. So they are powerful. So we can reduce training time using transfer learning. Then requires less labeled data. So not only reducing training time, but also it requires less labeled data. So if you have a limited dataset, if you have a limited training dataset, you can leverage a transfer learning model. You can bring a transfer learning model and train it on a small dataset, and it will also perform really well on that small dataset. So it terminates the need for large and huge amounts of data. Leverages robust general purpose visual features land on ImageNet. VGG's generalization ability has made it a trusted choice for practitioners even years after its publication. And now you can see the PyTorch, also the PyTorch library linked to their paper. So it's a standard or gold standard architecture in the industry, in the deep learning world. And also if you see here, we have the variants. We have VGG 11, VGG 11BN, VGG 13, VGG 13, VGG 16, and then we have VGG 19. And if you go, for example, to VGG 19, then you will be linked to VGG 19. Okay? Now let's get back. We can now go through this. So you can read through this if you want. But now we are discussing. Here we have this important concept of visualization and analysis. So understanding the internal mechanics of a deep network like VGG requires interpretability techniques that render its decision-making process visible. Visualization serves not only as a pedagogical tool, but also as a diagnostic lens into the network's land representations. Hierarchical feature extraction. VGG, by virtue of its depth and uniform design, demonstrates a clear progression of feature complexity across layers. So the earlier layers detect low-level features such as edges. So the convolution layer learns edges, the edges of the objects. So if you search in here, if you search for airplane, for example, images, airplane images, we have now, for example, this image. Let's go to this image. So, or this image. Now this image contains an airplane object. So the model, the early layers, the model try to detect. The model learns to detect at the very early layers. So in the earlier layers, the model tries to detect the edges. The edges are the borders of the object. So the borders of the object, or the boundaries, the limits, the ends of the object. So it tries to detect the edges, the ends, the limits, the borders, the boundaries of the objects. And then it learns the corners. The corners are the end of the object. So we have a corner. We have corners. Here we have corner. So it learns to detect these corners, these angles. Okay? These are really important, corners and angles, to define the shape, to define the structure of the object. Okay? Then we have simple textures. The texture is the region of the image where all the colors are the same. So here we have the same colors are going, white pixels. Then this is a changing or variable color. So this region all is called one texture, or is called a texture. A texture is a region in the image where all the pixels, all the colors of the pixels are quite the same. Okay, for example, this here is called a texture region, is a texture. Why? Because the colors are the same. Then when the model comes into here and learn this region, it says, oh, this is a different texture, or this is a different region. Okay, so the model tries to learn edges, borders, boundaries, and ends, limits. It tries to learn corners, angles. Okay, angles, corners, as we said, the angles here, these are angles, and it tries to detect the textures. These filters often resemble Gabor-like edge detectors or color blobs. Okay, so Gabor-like edge detectors are kernels, are called Gabor-like edge detectors. These kernels, if you apply them on your image, it will emphasize the edges. It will show you the edges. Then, when we reach intermediate layers, if we go up here, we have area layers. So these kind of features are learned here. This conv layer and this convolution layer. These detect the edges, the corners, and the textures. And then we have these convolution layers are considered intermediate layers. Okay, so these intermediate layers learn what features. If you go down, it tries to learn the capture more abstract patterns like contours. So the contours of the objects, shapes. So the shapes. So it tries to learn the shapes. So here, this shape is roughly a rectangle shape. So the shape of an airplane is roughly a rectangular shape. Whereas if you search for pizza images, then it will learn that the shape of a pizza image is circular. So it learns the shapes, the different shapes and complex shapes inside images, and textures common to object parts. And it also learns the color gradients. So the gradients of the color, it learns the brightness of the image, the contrast of the pixels, the saturation of the colors, the hue of the colors. Then we have deeper layers. Deeper layers represent high-level semantic features like the context of the image. For example, if you have a scene image that contains mountains and a person standing there, and you have a river, the model understands the context of the image and the scene, responding selectively to object categories or significant parts. For example, a dog's snot or eyes or ears. So it learns the eyes, it learns whole objects. It starts at the alias. It starts with low-level features, and then it progresses through the layers until it learns high-level semantic features that give us a semantic meaning. Okay, so edges alone don't refer to anything, don't give us a semantic meaning. But when they are combined together, the edges, the corners, the colors, they give us meaning. They give us a whole object that results into semantic and contextual meaning. We have activation maps. Activation maps are other names for feature maps. So you can say feature maps, or you could say activation maps. By capturing the output of individual convolution layers, activations, one can visualize which neurons respond most strongly to specific regions of the input. This highlights spatial regions that drive particular feature detections. So activation maps are the output of convolution layers, and as we said, capturing the output of individual convolution layers activations, and you can, or I can, one can visualize which neurons respond most strongly. Look, this is in bold font. It's important. Visualize which neurons respond most strongly to specific regions. So where is the most important region in this image? The most important region in this image is this region, whereas these are all noise. Okay, so the model, when the model applies some kernels on this image, it should emphasize these regions. It should highlight these regions. Okay, and it should focus on this object because it's the main content of the image. Here we have this airplane, so it has to focus on the image of airplane rather than focusing on the background noise, okay, the clouds. So you can visualize which neuron respond most strongly to specific regions of the input. This highlights spatial regions that drive particular feature detections. And we have GradCam, which is gradient weighted class activation mapping. So GradCam is short for gradient weighted class activation mapping. GradCam provides class specific localization maps by combining the feature maps from convolution layers with the gradients of the target class. This allows one to observe where in the image the model looks when predicting a particular class. So which region of this image was the most important region for the model to predict and also to classify. Okay, so you can visualize this via GradCam, which is gradient weighted class activation map. By combining the feature maps from convolution layers with the gradients of the target class, this allows one to observe where in the image the model looks. So where did the model look to make this classification? Where did the model focus to make this classification when predicting a particular class? And here we have an illustrative example. You can go through that. Given an image of a dog, shallow layers. The shallow layers learn highlight fair texture. It learns the highlight fair texture, contours and colors. As we said, it learns the lines, the stripes. So it tries to learn the lines. So these are lines. So the model focus on the lines, stripes to make classifications in the shallow layers. And then deeper layers show strong activations around the ears and nose. So the model starts to recognize objects as a whole, starts to recognize and realize objects as a whole. So it learns not just the specific features, but the whole structure and the whole building structure of the airplane. And as we said here, visualization doesn't merely explain what a network sees. It reveals how a network perceives, bridging the gap between computational operations and human intelligible interpretation. Okay, so visualization doesn't merely explain what a network sees. It reveals how a network perceives, bridging the gap between computational operations and human intelligible interpretation. And as we said, we have variants of the VGG. We have VGG BN, VGG, which is batch normalization. They applied BN, short for batch normalization. And we have VGG face. And we have also trained on large scale face datasets for facial recognition and verification. The model maintains VGG16's backbone, but is fine-tuned for human facial features. It's widely used in applications requiring identity verification or facial attribute detection. And we have Tiny VGG. Tiny VGG, in this workshop, we will build the Tiny VGG model. Okay, so we will focus on the Tiny VGG. Why? For faster experimentation, and also to train the model faster. Okay, but feel free to experiment with VGG19, VGG16, that contains this number of weights of parameters. As we said, VGG16 contains 138 million parameters. So if you can train that model, feel free to do that. But in this workshop, we will focus on building Tiny VGG model. And we have VGG as encoder. The convolutional portion of VGG is frequently reproposed as an encoder backbone in more complex architectures like fully convolutional networks, FCN, for segmentation, or UNet for biomedical image analysis. It's spatially aware. Its spatially aware hierarchical features make it ideal for dense prediction tasks. So the spatially aware hierarchical features of VGG makes it ideal for dense prediction tasks. And as we said, in this workshop, we will build Tiny VGG, a minimal VGG style network designed for educational purposes or deployment in low resource environments, often limited to two to four convolution layers and smaller filter sizes. Tiny VGG is used in beginner deep learning projects and real-time applications like mobile inference. So these variants affirm the modularity and transferability of the VGG design, allowing it to remain a foundational architecture long after its original formulation. Then let's move on to the practical walkthroughs to bridge the theory and implementation. This section guides you through applying the Tiny VGG in PyTorch. So we will use the PyTorch library to build and train this model. And also here we will not use transfer learning, so we don't need to freeze anything. We will build it from scratch, replicating the CNN explainer website. And now let's go down. Datasets. I used a custom dataset of 4 classes of food images, but you can feel free to try any dataset, whether you want to use a standard dataset like Cypher 10 class natural image dataset. Each image is 32 by 32 images, so the height is 32 and the width is 32. Upscale to 2 to 4 by 2 to 4. You can do that because why? This architecture, VGG Net, prefers or favors this sizing, which is 2 to 4, 224 by 224. So you can rescale that easily using PyTorch library. And now let's move on to the here. We have resources and ecosystem. So key papers, you can I will refer you to this key papers, which is the VGG Net paper. You can visit, and also, as we said, you can go from here to the paper and you can read through that. Feel free to read through it, okay, and see how they implemented it. And also we have here we have AlexNet and ResNet. You can refer back to them and see how many parameters they used and revise the architecture. Here we have the libraries. In this workshop we will use PyTorch library to build and train the model from scratch, and you can use of course, feel free to use TensorFlow and Keras. If you want to use TensorFlow, you could do that. Here we have practical resources, transfer learning notebook, GradCam visualization. So we will use GradCam. You can use the GradCam visualization to visualize the gradient cam, which is the feature map or the matrix that highlights where did the model look to make the classification. And then also you can refer back to this X-ray phenomena dataset. So this was a broad overview of the VGG architecture. I hope this was a simple one. Now we will dive into Google Colab and implement the VGG Net architecture on a custom dataset using PyTorch. So let's dive in, and happy machine learning. Hello everyone. In this video we're going to build a computer vision model, specifically an image classification model to classify different classes of food. We're going to build this project step by step, section by section, from getting the dataset towards building the model architecture, which is replicating Tiny VGG architecture, and then lastly we're going to make visual predictions using the model. So let's start and let's get started. First of all, we have to navigate into Google Collaboratory environment by going collab.research.google.com. So we have to go to this environment by writing in collab.research.google.com and then tap enter. You'll notice it will appear a window like this. We have to click on the new notebook button in order to create or instantiate a new collab. So click on new notebook and it will start a new notebook, as you can see. Now we have to connect. So once you are in Google Colab, you have to connect by going connect, as you can see, and it will connect. Also, we have to name it. So let's name it Building Computer Vision Model Image Classification Problem, and you can name it whatever you want. I have chosen this name, Building a Computer Vision Model for Image Classification Problem. Okay. Now, once we have connected, as you can see, it's now connected successfully. Let's now verify that we are connected by going print hello world, and if it runs successfully, that means we are connected. And as you can see, it printed hello world successfully. And also the second thing, we have to make sure that we have a GPU ready to go by going NVIDIA-SMI. Currently, we don't have GPU, okay? So when you connect, by clicking on the connect button here, Google Colab by default will not give you access to a GPU. You have to go to runtime, and from the runtime menu, you have to go change runtime type and then choose L4 GPU. As you can see, now we can click OK, save, and it will reconnect and connect us to the L4 GPU. We have to use a GPU. GPU is a hardware accelerator that will allow us to run models or to train models in a fast way, quickly. Now, if we get rid of these cells and then verify that we have a GPU ready to go by going exclamation mark NVIDIA-SMI, and yes, now we have a GPU. As you can see, we have NVIDIA L4 GPU. Okay, we have now NVIDIA L4 GPU ready to go and ready to build models. And you can see here the CUDA version. CUDA version is 12.4, and this report is printed in Friday, June 27. Okay, so now we have verified that we have a GPU. Let's now write a markdown here as computer vision with PyTorch. In this video, we will build a computer vision model with PyTorch library. We're going to use PyTorch library or PyTorch package to solve this problem. Okay, so in this notebook, we will use a subset dataset from the popular Food 101 dataset. Okay, so in this notebook, we will use a subset dataset from the popular Food 101 dataset. Specifically, we're going to use 4 different classes. The first one is sushi. The second one is cupcakes. The second one is cupcakes. The third one is macarons. And the fourth one is chocolate cake. So we will try to build a model to differentiate or to classify these classes: sushi, cupcakes, macarons, chocolate cake. So we will train a model to identify whether this image contains a sushi or cupcakes or macarons or chocolate cake, and then also we will try to get these classes correctly. So we want to train a model to recognize these different kinds of food. The first step now is we have to get data. So in order to build a machine learning model or a deep learning model, you have to get data. You have to obtain some data to be able to model it. So this data will be, as you can see, first of all, we have to import torch. So torch is a high-level library that will contain many different tensor operations, or will do many different tensor operations, and also contains data structures and tensor operations to apply these operations on the tensors, and then import, or from torch import nn. nn is a sub package or sub library inside the torch library that contains so many layers and contains so much of building blocks inside deep learning. For example, contains the convolutional layers, linear layers, and many different types of layers like ReLU layers, softmax layers, to build machine learning models. Now we have imported these libraries. We have to note PyTorch 0 or 1.10.0 plus is required for this course or for this video. So in order to build this model, you have to obtain PyTorch 1.10.0 plus. So you have to go torch dot _ version _ to verify that you have this version of PyTorch, which is 1.10.0 or plus. In this case, I have 2.6.0. So now we have 2.6.0 plus CUDA 12.4. So my torch version is 2.6.0 and CUDA version is 12.4. Now let's move into the next step, which is verifying that we have a GPU or CUDA device by going torch.CUDA.is available. So this function will return a boolean indicating if CUDA is currently available or not. So if this function returns false, that means we don't have GPU, and if it returns true, that means we are connected to a GPU. Now true, we are connected. We are truthfully connected to a GPU or to a CUDA device, and we have verified that using torch.CUDA.is _ available to verify that we have a GPU, and it returned true, indicating that we have a GPU or CUDA device. So let's set up device agnostic code by going device equals CUDA. So the string CUDA if torch library dot CUDA access the CUDA package dot is _ available. So if CUDA is available, if torch.CUDA.is available, then return CUDA, else return a CPU. So this code will verify that we have a CUDA device, and if we do have CUDA device, it will return CUDA. Okay, so now we have set up a device agnostic code, and we can make this as a markdown here. Okay, so set up device agnostic code, because we want our model to live on the device CUDA, and also we want our data to live on the device CUDA. Now that we have imported the required libraries, and also we have created or instantiated device agnostic code using this syntax in PyTorch, we can move on to getting the dataset. So get data, as we said, I have prepared a subset of the popular Food 101 dataset, which contains 4 classes: sushi, cupcakes, macarons, and chocolate cake. And these 4 classes, we will use them to train a model to try and recognize these different classes. So let's go get data. The first step is we have to import requests. So requests library will help us make a request over the internet, over the HTTP request. If you hover over it, you can see requests HTTP library. So this is a library to make requests over HTTP or over the internet. Okay, so requests is an HTTP library written in Python for human beings to use this library and then get some data from across the internet. Secondly, we have to import zip file. So we will get a zipped file and we have to unzip that file. So we need to import zip file in order to be able to unzip that file. Also, we have to from Matplotlib import path. We will construct paths in this tutorial. We will use the path class in order to construct paths and paths towards directories and folders. So we want to use the path class from the library Matplotlib. So from Matplotlib from Matplotlib import path, and also import OS in order to deal with the operating system of our Colab environment. Okay, now we have to set up data path, by going data path, the path of data, okay, variable. We have to create a variable called data path equals the class path, and then pass in the string data slash. So we want to create a folder here called data, and this folder will contain the images, the folders that contains the images. So we will instantiate a new object from the class path and then pass in here data slash. Secondly, we have to go image underscore path, so the path towards the image or the path that refers to the images, we have to go data path and then slash. So we are referring to the data path and then putting a slash and then name it as food images. So we want to create a subfolder or subdirectory inside the folder data path called food underscore images. So this step is important because we are defining our paths. So here in this step, we are defining our paths, the path towards the data folder and the path towards the food images folder. The second step is if we have to create an if condition. If the image folder doesn't exist, download it and prepare it. So now we will make a if condition. If this image folder doesn't exist in here, we have to download it and prepare it by going if image path.is directory. This function will verify that we do have an image path directory. So we have to call it .is underscore there is directory, and then if we do have this folder, let's print image path directory already exists, skipping download. So here we are skipping the download. Else, if we don't have this folder yet, let's print in here a nice message by going image path directory, okay, does not exist, creating one. Let's try to create a one. How do we create this folder? Well, we can go image path.mkdir. mkdir stands for make directory, and then let's pass in some parameters. Parents equals true. So what about if you have some parents to this folder? Well, true. You can create them by going parents, the parents parameter equals true, and then comma exist okay should be also true. If this folder exists, is it okay? Yes, it is okay, and then let's pass in true. So now we have finished writing the second step, which is verifying or making sure that we have image path already exist, that the folder image path already exists. If it does already exist, then print a message, image path, which is this path directory already exists, skipping download. Else we will print image path does not exist, creating one, and let's create a one using the mkdir function. The next step, after we have checked that our image path folder already exists, or if not, we will create a folder by going make directory parents true, comma exist okay equals true. The next step is we have to download the data zip file by going with open. Let's open a file, and then let's pass in a file. As you can see, we have to pass in a file parameter. So as data path slash, and then I will name this file food underscore images.zip, and this file we have to open it. This file currently doesn't exist here. It's not here. I am now creating it. I'm now making it up. So we have to open a file that doesn't exist before and name it as this name, food underscore images.zip, and we have to open this file in the mode of write binary as WB, as F. Now let's make a request by going request variable equals requests, I will use the requests library that we have imported in here. Import requests. So requests library. This library is used to make requests over the internet or over the HTTP connections or HTTP protocol over the internet. Okay, so we have to use this library requests.get and then get this URL, which I will type in here, https then :// then my academy name is Programming Ocean Academy dot S3. I have a bucket in S3, our services dot ap dash southeast dash 1 dot amazon aws.com / image classification underscore dataset dot zip. So as you can see, this is the link to my zip file, which contains the zipped version of my dataset. Okay, contains the zipped version of my dataset. Now let's try and print a nice message. For example, downloading the data or food images data dot and then we have to access the file, which is this file food images.zip. We have to access this file by going the f variable dot write. We have to write on this file. I want to write on it the request that I am making in this variable, the request. Okay, so we have to type in request.content. So the content, whatever the content is of this zipped version, let's write it to this new opened file. So we are opening a file called foodimages.zip in the write binary mode, and then we are naming it as an alias name f. So f file dot write, I want to write to write in this file the request content, the content returned from the request that I am making using the requests library. Okay, so this process is funny. And then the next step is unzip data file, which is .zip. We want to unzip this file by going with, we have to write a with context manager, or we have to use the with keyword in Python with zip file. So now I am using the zip file library, which is in here, import zip file. So I want to import zip file in order to use the features and the functions inside zip file library. So you have to import this library. Import zip file will help you unzip .zip files. So let's now use this file, zip file .zip file class. We want to employ a class called zip file, as you can see, zip file, and let's pass in the file path, the zipped file, the zip file, which is in data path folder / and then its name is food_images.zip, the same name as in here. So food_images.zip, and let's open this file this time using the read mode as R. R refers to the read mode. So I want to read this file and then refer to it as zip reference, the reference to the zip file, and let's print in here unzipping food images .zip file. Okay, dot, and let's now refer to zip reference or access the zip ref variable dot extract all. We have to extract all the items, as you can see in here, this function extract all members from the archive to the current working directory. So it extracts all members from the archive to the current working directory, and let's pass in the image path, image_path. Okay, let's now run this cell, and as you can see, data / food images doesn't exist, creating one because we don't have that folder, and then downloading food images data, it it downloaded the food images data to the dot, and then unzipping the food images .zip file and unzipping its members into the current working directory, which is the image path. Now we have if you refresh in here, we have a data folder. Inside it we have food images, and then if you open this folder, we have a folder called dataset. Inside this folder we have two folders. The first one is train, and then inside train we have 4 classes. As you can see, we have chocolate cake, cupcakes, macarons, sushi. For example, if you open chocolate cake, we have a whole bunch of images, and now it's trying to open the folder. As you can see, it will show us the images inside this folder. Now just one thing, we want to get rid of this zip file. You want to delete it, okay? So you can go OS, which is the OS library dot remove, and then pass in the data path slash food images slash food underscore images dot zip. So we can get rid of this file, and let's run that. Or we have typed in food underscore images dot zip, data path slash food images slash food images, or we can copy the path of it and then pass it in here in string format, and now it has removed this file. If you refresh again, there's no anymore a zip file inside the food images folder. So now we have a folder dataset. Inside it we have train, and then inside train we have this folder which contains these images. Okay, so now if we open this image .jpeg, we have this image which is a chocolate cake. The second image is this image, and so on and so forth. So we have a whole bunch of images here inside these folders, and as you can see, we can scroll down. Now let's familiarize ourselves with the dataset structure. Let's get used with the structure of the folders. This kind of structure is called the standard image classification format. So when we have a data folder, inside it we have a folder called food images. Inside this folder or directory, we have a directory called dataset. Inside this directory, we have 2 folders or 2 directories. The first one is train, which contains the training images, contains the training photos, and the second one is called test, which contains the testing photos, the testing photographs. In each one of these test and train folders, we have 4 folders. So we have 4 directories in the test folder, and also we have 5 or 4 directories inside the train folder. For example, the folder cupcakes contains the images that relates to this class. These images all relate to the class cupcakes, okay? And the images that are inside macarons all are related or are associated with the macarons class, and so on and so forth. So when we have an image inside the sushi folder, it is related to a sushi class, and so on. So this architecture is called the standard image classification format. Let's write in here a markdown. Nice. Now we have gotten a data set in our environment successfully in the standard image classification format. Standard image classification format, which goes like this. We have a folder data, and then inside this data we have another folder called food images, and then inside this folder we have a folder called dataset. Inside the dataset we have 2 folders. The first is train and the second is test. Inside train we have class A and class B, and so on so forth, class C until the end. Okay, so this is called the standard image classification format. Data, and then some folder, dataset, that contains train folder, and the train folder contains class A, class B, class C, and the same thing goes for the test. We also have the same structure for the test. We have inside the test directory, we have class A, class B, class C, and inside each class we have a number of images that relates to that particular class. The next step is we have to set up a directory path. So set up directory paths, which is the train there and the test there. So let's go train underscore directory equals image path, then slash dataset slash train, and the same goes for the test directory equals image path slash dataset slash test. So this train directory equals image path. The image path refers to the food images folder, which is in here, food images. Inside this folder we have dataset folder. As you can see, inside the dataset folder we have we have two folders. The first is train and the second is test. So we are accessing those paths by going slash train and then slash test and assigning them to these variables, train there and test there. Let's run that. Train directory, we have a POSIX path, data slash food images slash dataset slash train, and also we have the same thing for the test directory. We have data slash food images slash dataset slash test. As you can see, data slash food images slash dataset, here the same, slash test, and the same goes for the train. So we have set up our directory paths. Now let's familiarize ourselves with becoming one with the data. So let's go. Becoming, the second step after we have got data is becoming one with the data, which is data preparation, and data exploration. So we want to do some data exploration. We want to explore the dataset. We want to familiarize ourselves with the dataset by walking through the folder system or the folder structure in here. We have a helpful function inside the OS library, which is called a walk. So let's import OS. We have done that before, so it's optional here, but we are notifying that we need OS library. So let's go import OS. I know I have imported it earlier, but now I am indicating that we need to import OS to do this step. Let's define a function called walkthrough directory, and then let's pass in a directory path. So we need to pass in a directory path in here, and this function will walk through each of the folders, each of the files, and retain some helpful information about the directory structure. So let's go. This function, what it does is it walks through directory path, dir path, returning and returns its contents. Okay. So let's construct a for loop for directory path, for each directory path, comma, directory names, comma, file names in os.walk. So notice we are using the nice function walk. This walk function is a great function, os.walk, and then let's pass in the directory path. Now for each loop, for each iteration, let's print in here, there are this length of directory names and also directories, and length of file names, images in this directory path. So this syntax sounds a little bit confusing, but it's simple. Now we have a function called os.walk. This function, what it will do is it will retain the content of the folder. Let's pass in the folder, for example, the data path folder, data path, and let's run this. It retains a generator. If we turn this generator into a list, it will retain information about the contents of the folders. These information are as the following. we have a list. Inside this list, we have tuples. Each tuple contains a folder. First of all, we have a data directory. Then we have data/food images directory, which contains one directory, dataset. And then the dataset directory contains two directories, train and test, and so on and so forth. And the train contains four directories, sushi, cupcakes, chocolate cake, macarons. We want to loop through this information by going for directory path, comma, dir names, comma, file names in this, and then we want to print this message. There are this length or this number of directories. Now, the first one, there are one, there are two. These are numbers from here. So inside data, how many directories do we have? We have one directory. Inside food images, there are one directory. Inside dataset, we have two. As you can see, we have two directories. We have two folders, train and test. And then inside train, we have four. Chocolate cake, cupcakes, macarons. So there are four directories. And then there are zero, because inside chocolate cake, we don't have any folder in here. We just have files, images files. So there are zero, and then inside test, we have four directories, and then 0, 0, 0, 0. Okay? Then let's write in here directories like this, and the length of file names, let's get the length of the number of files. As you can see, we have this number of images. So we have here 0 files, and then we have here inside this directory we have 250 files, and let's pass in here in this directory path. So this is a breakdown of what this function walk could help us learn. Now let's try to run this function after we have explained it. Walk through directory, and let's pass in the image path. It will return this information. So we have an automatic function that will run this function os.walk automatically behind the scenes. Let's focus now on the important information. There are 0 directories, and we have 250 images inside food images. As you can see, inside the food images directory, and then actually we want to use here dir path without using a underscore. Okay, so let's run this. Now, as you can see, we have 250 images inside the sushi folder. So we have 250 images, training images for sushi. We have 250 images, training images for cupcakes. And also we have 250 images, training images for chocolate cake. And we have 250 training images for macarons. So we have 250 images or 250 images for each training class, sushi, cupcakes, chocolate cake, macarons, and we have 75 testing images for each one. So we have 75 images testing for sushi, and we have 75 testing photos for cupcakes, and we have 75 testing pictures for chocolate cake, and so on and so forth. So we can familiarize ourselves with the number of files, number of images, number of photos, and also the directory names, the directory structure, using this helpful function inside the library os.walk, and then pass in the directory path. Okay, so now we have learned something from this. The next step is, let's move on to the next step, which is set up train and testing paths, which we have done earlier. So we have train directory, which is this path, and also we have test directory, which is this path, data/food images/dataset/test, and the same goes for the train. Now the next step is we have to visualize some data. So let's visualize some data here. Let's import random, and then so the random library in Python helps us generate random numbers. And then let's from pill import image. Let's import the image class from the pill. Pill is a library inside Python, which stands for Python Image Library. So pill is shortcut for Python Image Library. This library is the standard library in Python, which deals with images, deals with image files, with pictures, with photos, with photographs inside the Python programming language. So we have from the PIL library, let's import the image class, as you can see, and then let's get all image paths. Get all image paths. This step is really interesting. Because why? Because we are going to choose randomly one image from a list. So let's go image path list equals list, and then we want to use the image path directory or path dot glob. So the glob function will glob all the files. Glob, in other words, grab. So grab all the files, all the images from this pattern. Every single image that fits this pattern. So any file that fits within this pattern, it will get it. The pattern here will be star slash star slash star. So image path is image underscore path, okay, which is the food images. We want to get star and then slash star and then slash star.jpg, as you can see. Now let's print this image path list and verify that we have gotten these files. We have an empty list slash star then slash star. Now we have gotten the files. Why? Because we have to go star, or meaning all of the files inside the food images, and then star all of the folders in here, dataset, slash star whether it was training image or testing image, and then slash star from any directory, whether it was chocolate cake or cupcakes or macarons, then slash star.jpg. It will get all of the images from inside these folders. Okay, so we have now we have a magnificent huge list of images, as you can see, that contains all different images, whether it was training images. So we have train slash sushi, then we have, if you scroll down, we have train slash cupcakes, and the same goes on. So we have a list, a long list, a large list of all images, all training and all testing images from inside. As you can see, if you scroll down, we also have a test version, but we have here the dot, meaning we have a lot more elements, but it can't show them all in here. The next step is pick an image or pick a random image from image path by going random underscore image underscore path. So we want to pick random image path equals the random library, and then we want to use the choice function. So the choice function, choose a random element from a non-empty sequence, and let's pass in here the image path list. So now the third step is get image class from path, get image class from path, which is path name. The image class is the name of the directory. The image class, the class of the image, is the name of the directory, where the image is stored. And then let's go ahead, image underscore class equals random image path dot stem, or dot parent property dot stem. The stem is the last thing in here. Here we have, for example, this image. This is the name of the image. Dot parent will get this, and then stem will get just this stem, this root, the root name. Okay, so stem is another word for root. If we check here for this random image, if we comment this and then print this random image path, we have this random image path. So this is a random image. If you run again, we will get another random image. As we run, we will get random images. So now we have a chocolate cake image. Let's run again. We have another cupcakes image. Okay, let's now get dot parent. Now you'll notice that this image name will disappear. It will just end in cupcakes. Sushi, for example, sushi, macarons. So just the parent name, the name of the folder. If we try to get the stem, it will just retain the name of the image, whether it was macarons, chocolate cake, and so on, so on. So now let's move on to the next step, which is the fourth step. Open image by going image equals image class, this class image dot open, and then let's pass in random image path. The fifth step is print metadata. Let's print some metadata about the image. Print random image path, and then random underscore image path to know which image that we are printing. Then image class, the class of the image as image underscore class. Then print f string image height. Let's print the height of the image dot height, and then print f string image width. Let's know what is the width of the image by going image dot width, and then let's show the image using the pill library. Now we have a macarons image. So as you can see, we have printed some metadata. Random image path, this is the random image path, and then image class, the image class is macarons, and then image height, the height of the image is 289, and the width of the image is 512. If you run again, we will get another random image. So now we have random image path, which is this path, and then image class is cupcakes, image height as 384, and image width is 512. So this mechanism is using the Python image library. Now let's use Matplotlib to plot these images. We can go to the next step now by using Matplotlib. So import NumPy as NP. We need the NumPy library, and then import Matplotlib. Matplotlib is a important library for visualization in Python, for making visualizations, nice visualizations in Python language. And also we have to let's turn the image into an array. So in order to be able to visualize this image using Matplotlib and not just using the Python image library, okay, so we can visualize images using two methods. We have two methods, two kinds of ways to visualize images. We can use the Python image library, the Python imaging library, which is PIL, to visualize images, and also we can use Matplotlib. So let's use Matplotlib, and in order to use Matplotlib, we have to convert this image from PIL into NumPy array. So let's go image as array, variable image as array equals NumPy.array. Let's convert this image into an array, and then or NumPy.as array. Okay, let's pass in here the image that we have in the above cell, and then plot the image. Now plotting the image is really simple. With Matplotlib, we can create a figure, plt.figure, and then specify the fixed size. Fixed size equals 10,7. You can specify it as whatever you want. plt.imshow. Let's imshow the image. Let's image show it. Okay, image as array. And then let's go plt.title. Let's specify a title here as f string image class. So the class of the image, we have image underscore class, and then image. I have run that cell. I have run it. Okay, image shape. So in a wrong way, I have clicked enter. I was intending to write image class or image shapes as image as array dot shape, and then this shape will be as height, comma width, comma color channels. So we have height, the height of the image, the height of the photo, width, the width of the photo, and then color channels. And this is called the HWC way, which is height, width, color channels. Now let's show the image. Let's first turn off the axes. So this axis, that's nice. We have axis here. We can turn off these axes. Okay, and then plt.show. Let's show this image. Let's run that cell. Now we don't have axes anymore, and you can see image class is cupcakes. Image shapes, we have 384. The height of the image is 384. The width of the image is 512, and the number of color channels, we have 3 color channels, as you can see. If we run this cell again, we will get a different image. okay, Macron's image. And then if you try to visualize it with Matplotlib, we will get this image inside Matplotlib, as you can see. Okay, now let's visualize this image as array to indicate that we can convert these images into arrays. We can show data and then visualize this image the other way, which is the array version. Now this is an important concept. Every image or every photo, every photograph, every picture we have in the digital form, meaning inside computer, this image could be represented as an array. So we can represent this image as an array. We can convert or turn this image into an array format which contains numerical values, numbers or integers, floats. So we can convert the image from, these are pixels. So we have pixels, colors, and these pixels are represented by colors, and each color is represented by a value of red, green, blue, and we can store these values inside an array, or we can have these values in an array. And converting images to arrays is important. Why? To be able to create models, to create and train models. Models or machine learning models don't understand images as images. We must convert these images into arrays, into tensors, to be able to handle them with a machine learning model or with a deep learning model. The convolution network doesn't understand images as images. They want to deal with arrays, or they prefer to deal with images as arrays, as numbers, as numerical formats, as numerical form, numerical representation, to be able to learn patterns or learn the features, the edges, the corners from the numbers. Not as humans. We as humans prefer to look at images from the image way. Okay. Now we have visualized some images from our dataset. You can also run it again, and you will get a different image. If you run this again, every time you run it, you will get a different image, and then you can visualize it with Matplotlib, as you can see. Okay, and also notice here, image as array, we have here numbers. If you run this again, remember we have 19, 15, 16. Run it again. Now we have 157, 91, 65. We have a different combination of pixels. Let's move on to the next step, which is transforming data. So transforming data. This step is really important. Really important. Why? Because now we want to apply some transformations on the data. So transforming data. Before we can use our image data with PyTorch, so before we can use our image data with PyTorch, before we can use our image data with PyTorch, we have to do two things. First of all, we have to turn our target data into tensors. Why? In our case, numerical representation of our images. And then the second step is turn it into torch.utils.data.dataset, and subsequently a torch.utils.data.DataLoader, okay, the DataLoader object. We will call it, or we will call these two as dataset and DataLoader for short. Okay, so in order to be able to use these images with our models, we have to turn our target data into tensors. We have to represent our images in a tensor format, numerical representation of our images. And secondly, we have to turn it into a dataset and subsequently a torch.utils.data.DataLoader, and we will call these two dataset and DataLoader. So let's proceed into these steps. First of all, import torch. Torch, as we said, this is a high-level library that contains tensor or data structures. If you read from here, the torch package contains data structures for multi-dimensional tensors and defines mathematical operations over these tensors. And the second thing is import or from torch, let's go from torch.utils.data import DataLoader. We have to import the DataLoader class to convert our datasets into data loaders, and also from torchvision let's import datasets, transforms. Let's run that. Okay. Now I want to go to torchvision. We have inside PyTorch, we have domain libraries. So we have domains in machine learning, in deep learning. We have domains. We have vision, we have text, audio, recommendation. Luckily, PyTorch has a library for each one of these domains. If you go to, for example, documentation, and then go to PyTorch domains, we have the domains as you can see in here. We have torch audio, torch tune, torch vision, which we will use in this video. We have torch rec for recommendation engines, torch codec, torch data, and torch RL, torch dict, and also we have PyTorch on XLA. XLA stands for Accelerated Linear Algebra Devices. In this video, we will focus on this torch vision. We are dealing with a vision problem. We are solving image classification. We want to classify images. So torch vision, this library is part of the PyTorch project. PyTorch is an open source machine learning framework. The torch vision package consists of popular datasets, model architectures, and common image transformations for computer vision. That sounds interesting. Let's go into it. Now, if we read into here, this is important, really important. Torch vision. This library is part of the PyTorch project. PyTorch is an open source machine learning framework. The torch vision library contains over here 4 things. We have transforming. This library contains every single transformation you can imagine in deep learning. So all kinds of transformations, whether it was photometric or geometrical or resize, any transformation, it exists into here. Transforming and augmenting images. So transforming images is an important part in this lesson, and we of course we want to transform our images to be able or to be in the size that we want. So we want to resize images. Also, we can apply some random color operations like scale jitter. Scale jitter manipulates the, if you look into here, the scale jitter manipulates the perform large scale jitter on the input according to this paper. Simple copy paste is a strong data augmentation method for instance segmentation, applies a scale jitter operation on the images. And also we can apply a whole bunch of different transformations in here. And also, secondly, we have models and pre-trained weights. So we have models and pre-trained weights that we can use and leverage in our deep learning projects. For example, if you scroll down, we have classification, we have AlexNet, ConvNext, DenseNet, EfficientNet, GoogleNet, Inception, Max Vision Transformer, ResNet, ShuffleNet, and so on. We have also Swim Transformer, VGG. So these are all pre-trained models that we can leverage in our problems. Also, we have datasets. Datasets, this is a combination of the most gold standard datasets inside deep learning, like the Cypher 10 dataset. Also, we have Cypher 100, an extension to that. We have also EMNest, FashionMNest, and so on and so forth. So we have all these datasets available, okay? And also we can use base classes for custom datasets, which is in here. These 3 classes are base classes for custom datasets. What if you don't want to use these datasets, but instead you have a custom dataset that you want to leverage? Well, then luckily PyTorch provides us with this class, ImageFolder. We can apply this class in order to read images from our own custom dataset. So this is a high-level overview of the torch vision package. Again, you can access that from docs, PyTorch domains, and then go to torch vision, and then you have all these features in here: transformations, models, datasets, also decoding, encoding images. An important one for making predictions. We will use them when we make predictions on our images. So now let's return back to our notebook and let's transform our data. So transforming data 3.1, transforming data with torchvision.transforms. We want to use the transforms library. So transforms help you get your images ready to be used with a model, perform data augmentation. Okay, now let's write a transform for image. Let's go. Data transform equals transforms library dot compose. So compose is a class that lets you compose or composes several transforms together. If you want to chain several transforms together, if you want to put multiple transforms together in one hit, you can use the class compose. The class compose combines different transformations into a single pipeline. So this is called a transforms pipeline. Let's pass in a list here. This list takes from me several transforms. The first one is transforms, which is, let's put a comment here, resize our images. Let's resize our images to 64 by 64. So we have to, in order to replicate, in this video, we will replicate CNN Explainer website. And if we notice here, this website contains the Tiny VGG architecture. Okay, so wait for that to load. So we have a convolution layer, ReLU, convolution, ReLU, max pool, conv, ReLU, max pool. Let's try to replicate this Tiny VGG architecture. And if you notice here, we have the input as 64 by 64 by 3 channels. So if you want to replicate this Tiny VGG architecture, we have to resize our images into 64, the height, comma, 64, the width, comma, 3 channels. So let's do that by going transforms dot resize, and then pass in the size as 64, 64 as that. So the resize operation will resize our images into the size 64 by 64, comma, let's flip the images randomly. Let's try to flip the images randomly on the horizontal axis by going transforms dot random horizontal flip, and we will use this class random horizontal flip. Let's pass in here the probability as 0.5. So 50% of the time we want to flip our images. Okay, not all the times, but 50% of the times. So this is the probability of flipping an image, comma, turn the image. Let's turn the image into a torch.tensor. Let's convert the image from the image format into a tensor format by going transforms dot toTensor. This class will convert our images into tensors. Now we have a nice, great pipeline that will transform our images in 3 transformations: resizing them into 64 by 64 size, random horizontal flip, and also toTensor. Let's now apply this transformation on our image. Now, if you recall, we have an image, which is this image. Okay, now we have this image. Let's try to apply this pipeline on it. How to do that? Well, it's really simple. Just you have to call this variable or this composition data transform, data underscore transform, and then pass the image to this transform. Now you'll notice this image will get resized, will get flipped, and also will get converted into tensor. Let's run that, and we have a tensor that is flipped and also resized. How to assure that? If we check the shape of it, dot shape, we will get 3 by 64 by 64, which is resized. So now the height of the image is 64 and the width is also 64. So it is resized. Okay, so this is the first transformation happened. What about the second one? Random horizontal flip. Well, if you want to know whether your image is flipped or not, you have to visualize it. So let's visualize it. in a Matplotlib figure, plt.figure. Let's create a figure, and that's a good practice. Fig size equals 10,7. plt.imshow. Let's image show this image, and then plt.axis of plt.show. So now, if you notice, this image is now resized. It has a low resolution now, and also it's flipped. How to assure that it's flipped? Let's print the image, the original image. Notice the direction of the cake is towards this section, and the direction here is flipped. Okay, so the image is flipped. Notice the direction is now flipped. Okay, every time it will be flipped in a different direction. Okay, now if you want to assure that this image is converted into a tensor, well, as I told you, when you apply a transform over the image, data transform, and then pass the image, we have a tensor. Okay, so we have converted the image into a tensor. Now let's move on to the next step, which is now we have transformed our images successfully. Let's get the image path list. We recall we have an image path list, a long list of images. We can use that and apply whatever image of this on the transform. Let's now define a function that will show the difference between the original image and the transformed image, which is a simple function. Let's go define. Let's define this function, define def, which is called plot transformed images, and let's pass in the image paths, the paths of the images as list, comma, transform, the transform, and then comma n, the number of images as 3 images in a time, seed equals none. We will initialize the seed as none. This image will do the following. It will select random images from a path of images, and loads / transforms them, then plots the original versus the transformed image or version. Okay, so it was this function does nothing but selects random images from a path of images and loads / transforms them, then plots the original versus the transformed version. Let's go if seed, let's set random dot seed as seed. Okay, and then if for, let's construct a for loop for image path in random image path. So we have random image paths, which is this variable that I have to correct in here. Random image paths equals random dot sample. So we want to sample from the image paths the k equals n. So we have a library called random. We have the random library inside Python. This library contains a function called choice. We can pass in here a sequence, for example, the image path list, and it will choose a random image. Every time it will choose a random image. Also, there's another function called sample. This function will, if we pass in here a k, so k equals 1, it will choose also one image. But notice inside a list, this function is different. This function will not choose one image, not choose just one choice, but instead will give you, for example, 2 images or 3 images, however many images you want to sample from the population. So the sample function is chooses k unique random elements from a population sequence. So this function sample chooses k unique random elements. In this case, we have 3 k unique random images, random image paths. We have chosen them from a population sequence. So if you pass in here a sequence, it will choose, for example, 10 random images at a time. Every time it will choose 10 different random images. It will sample them. So taking samples from a population, and the number of samples you have to define yourself. So random.sample, and then pass in k equals n. Let's pass here n, and n is a parameter over here, equals 3. So k equals n. N is a parameter over here, equals 3. For each image path in random image paths, let's go ahead and open this image with image class dot open. Let's open this image and then pass in here open image path, image underscore path as f. Okay, and then let's create a figure, fig comma ax equals plt.subplots, pass in here n rows equals 1 comma n calls equals 1. So we want to show one row and the number of columns is 2. The number of columns should be 2. So n calls equals 2. N calls ax at index 0 dot im show. Let's image show the f, the image, and then ax at index 0 dot set title. Let's set the title as original, the original image, original \n, and then let's type in the size. We want the size. What is the size of the image? As f.size, because if you have an image here, for example this image, if you choose a random choice, random.choice from image path list, you will get this image. If you try to open it using the Python image library, image class, and then pass .open, pass this choice, it will open an image, and then if you get the size, it will give you the size. The size of the image is 512 by 512, and every single time it will give you the size of the image. So the size attribute access the size, or gives you the size, provides you with the size of the image, the height and the width, 512 384. Whether and if you don't access the size, it will visualize the image. Okay, so f.size, and then ax at index 0 dot axis. Let's turn off the axis. So this is a simple function, axis. Let's turn off the axes as false, and then let's transform the image and plot target image, plot target image. Transformed image equals transform that we have to pass in here, the transform in here that we pass in here into here, transform, and then apply this transform on the image. F dot permute, we have to permute it 1, 2, 0 in order to be able to plot it with Matplotlib. Ax at index 1 dot im show, let's image show the transformed image, transformed underscore image, and also ax at index 1 dot set title. Let's set the title of it as f string transformed, and then \n, new line, shape, the shape as transformed image dot shape, and then ax at index 1 dot axis. Let's turn off the axis, and now figure, let's set a super title. This is a not subtitle but a super title as f string class. The class of the image will be as image path dot parent dot stem to get the class name as we did before, then comma font size equals 16. Now this function will show us a pretty figure. If we call this function now plot transformed image, and then pass in here image paths equals image path list, comma transform. The transform that we want to apply is data transform, comma n equals 3. I want to show 3 images, comma seed equals none. Now let's run this function call, and it shows us this image. As you can see in here, on the left hand side we have the original image, which is 512 by 384, and then we have the transformed version. The transformed version is 64 by 64 by 3 cat channels, and also we can see that the image is now resized. The image is also flipped. Okay, the image is flipped because here, if you notice here, the cutting is in a different direction. Also here we have a class macrons, and the image is also flipped. As you can see, the image here is flipped. It's towards the other direction. Okay, and here class sushi, we have a class sushi. Also, if you want to run again, you will get different set of images. Okay, so here the image is clearly flipped. Okay, so here the class is sushi, the transformed version is 64 by 64 by 3 cache channels, and then we have class cupcakes in here. As you can see, the image is resized and so on and so forth. Of course, you could play around with the transform in here. So you could apply different transformations. For example, you could apply a transform like transforms.random perspective, and this takes from us a distortion scale as 0.5. Let's keep the default settings as it is, and let's run again. And now let's check these images. We have random perspective on the images. Okay, so we can see here we have class macros. As you can see, this is a random perspective transformation as shown in the right hand side, which shows this side shows the transformed version, the transformed image, and this section shows us the original image. So this transformation is called random perspective. It randomly shows us different perspectives of the images. Oh, and you can also feel free to try different transformations. Also, last try, let's try the random rotation, and then let's rotate the image as degrees equals, for example, 180. Let's run that again, and let's try this transformation to make sure that we have this function dynamic. So we can see that the image now is rotated. So I have a rotation. This image is a macrons. It's now rotated, and if you scroll down, we have also this image rotated. So see here we have class sushi. This image is now rotated. Okay, so we can play around with that. As you can see, we can try different transformations. Currently, I will keep the random horizontal flip transformation, and then let's run this function the last time. It shows us these images. Okay. Now option 1. Now we have two options to read dataset. We have option 1 and option 2. I will go with option 1 because it's simple. Okay. So let's go with option 1, loading image data using ImageFolder. So now I want to read images. How do we get? Now we have a question, a very important question. Now we have a way to transform our images into tenses, and we have discussed that using this transform composition to tensor. This function converts our images into tenses. But how do we convert? Now we are converting the images individually, image by image. So we are converting these images into tenses, image by image. If you visualize this image variable, we have an image, and if we apply the transform, the data transform on it, I will get a tensor. But this transformation happened on one image. What about if we want to get, or if we want to apply this transformation on every single image in our directories, on every single image in our folders? How do we read images? How do we grab these images and apply a transformation on it? Well, that's using the ImageFolder class. So I mentioned earlier that inside datasets here, if you go to datasets and then go to this is a very, very, very important section. Base classes for custom datasets. If we click on that, it will navigate us to this section. We have a very important and great function called ImageFolder. This function is really, really great and significant. A generic DataLoader where the images are arranged in this way by default. So this way is called the standard image classification format, where we have a root directory, and inside that root directory we have a class, for example dog. If you are dealing with animal classification, for example dog versus cat classification, dog/xxx.png. So this is a random image xxx.png, and then we have xxy.png, xxz.png, and so on and so forth. So we have images inside the dog folder. Also, the cat folder contains images. 123.png, nsdf3.png, and asd932.png. So if we have our datasets, if our dataset exists in this format, exists in this structure, we can use this class ImageFolder to read the images, to select the images, to grab the images. So it's a generic data loader where the images are arranged in this way by default. So let's now use it. Let's go ahead. Now we have a train directory, okay, which is data slash food images slash dataset slash train, and we have test directory. We can read images from these folders or from these paths. Let's go use ImageFolder class to create datasets. We can go train. So from torchvision import datasets. So from torchvision import datasets, and then train data equals datasets library dot image folder. Okay, so inside the datasets library inside the torchvision, we have a class called ImageFolder. This class will help us read images or select images, grab images from inside folders. We have to pass in root, the root in here as this. So we have root or string or path, root directory path. So we have a path leading towards the root directory. So let's pass in here root equals train directory, comma, transform. Let's apply the data transform, which we have defined up in the above cell. Data transform, we have a compose transform, resize, random, horizontal flip, and we have two tensor, and we can scroll down, and now we can apply also, we also can apply target transform as none, but in this case I will specify it as none. So target transform equals none. Test data, we can do the same thing for the test data, equals datasets. So we want to use the datasets package dot image folder. This class, as I said, helps us read images or selects images, grabs images, or even fetch images from inside directories. So image folder, and then pass in root equals test directory, comma, transform equals data transform, comma, target transform, target underscore transform equals target transform equals none. Now let's run this cell. We have now created our datasets. If you want to visualize them, let's go train data. We have a dataset, as you can see. We have read a dataset, or we have created a dataset using the image folder, using image folder class. Number of data points, we have 1,000 images, so we have 1,000 images for training, and root location as data slash food images slash dataset slash train. So we have this path, data slash food images slash dataset slash train. Standard transform, we have a composition of transforms, resize, size equals 64 by 64, random flip, and also two tensor. So now we have created a dataset for train data and also a dataset for test data. So test data, we have a dataset called ImageFolder. So as a revise, we have from torchvision import datasets, and this datasets library contains a class called ImageFolder. This class helps us to fetch images from inside folders, to fetch or grab images, okay, from the train directory, from the train there directory, comma, and also we want to apply the transform, which is data transform. This transform, I want to apply a resize, a random, horizontal flip, a two tensor. I want to apply these transformations on every single image fetched or grabbed from this directory. And then target transform equals none, because I don't want to, here we don't want to transform the targets of our images. So if you want to apply any transformation on the targets, The targets are labels. In other words, labels or outputs or outcomes. You can specify a function here, but currently we don't want to specify any transformation or any adjustments to the targets. So target transform equals none. For the test data, the same thing. Datasets.ImageFolder. As we said, this class helps us to retain images, to select images from the test directory. Transform equals data transform, and then target transform equals none. Now, what if we want to access the first index, okay, of this trained data? We can go at index 0. It will retain a tuple of the image tensor and also the associated label and its associated label, its corresponding label. This label is 0. 0 refers to the, for the class name, which is the model has, or the library has chosen for 0 to be. If you want to know, you can access the get class names as list as class names equals train data object dot classes. So classes attribute will retain a list of the classes and we can access them via class names. Now we have at index 0 we have chocolate cake. So if you see a label 0, that means a chocolate cake. So we have converted our labels into numbers, into numerical formats. So now our labels, the model doesn't understand chocolate cake. The model also doesn't understand cupcakes. It understands numbers. It understands numerical formats. So we have to convert our labels, our targets, into numbers, and we have done that. Secondly, also we have converted our images into tenses. Also we can get class names as dict, class names as dictionary via class underscore dict and then train underscore data, the train data object dot class to idx. This property or this attribute will give us a dictionary of the classes mapped to indices, mapped to indexes, for short idx. So class dict, we have this dictionary. Notice this is a list, but this is a dictionary. In Python, this is called a dictionary, which contains chocolate cake mapped to 0, cupcakes mapped to 1, macarons mapped to 2, and sushi mapped to 3. So the label 3 is mapped to sushi. The label 2 is corresponding to macarons. The label 1 is associated with cupcakes, and so on and so forth. So the model will refer to cupcakes as 1. The model will also refer to macarons as 2. Okay? Check the lengths of our dataset. We can check the length of trained data and also the length of test data. So how many training images do we have? We have 1,000 images. So we have 1,000 training images. And the length of test data, we have 300 images. 300 testing images. Okay? And also we can access the trained data, the targets, and it will show us a long list of the targets. As you can see, the targets are the labels. PyTorch prefers to refer to labels as targets. So targets are the labels. So 0, 0, 0, which is chocolate cake, chocolate cake, chocolate cake. So the class 0 is chocolate cake. And if you scroll down, it will move on to 1, 1, 1, 1. So these are all the labels, all the targets, all the correct outputs for our training data. Okay? As you can see, 2, 2. So this is a huge list containing the labels or the targets of our data. The same thing goes for the test data. We can go test data dot classes. It will retain a list of the class names. Now the question here, from where did the class image folder get this class image folder? From where did it get the names of the folders? Well, the class image folder infers the names of the folders from these folders: chocolate cake, cupcakes, macarons. So whatever you refer to the class as the directory name, this directory name is very important. The name of the directory is really, really important because the images will relate to this class name, to the directory name. Okay? So you have to be careful when naming your folders names. You have to name them in the correct way. For example, here we have this folder cupcakes. This name will be taken to be the label or the target, the output, the outcome for all of these images. So the class image folder infers the class names from the directory names. And now we can get the image, label using this syntax, train data at index 0. As we said, train data is a dataset. It's a dataset object. We can index on the 0th index. We will get a tuple of a tensor and its corresponding label. And now if you access at index 0, we'll get just the image tensor. And then we can access the train data at index 0, at index 1, we will get also the label. Then we can unpack these values inside image, label. Now we'll have an image variable, image, which contains this tensor, and label, which contains the label for the image, which is 0, chocolate cake. Okay. We can also visualize this image if you wanted to, but now let's keep going down and let's print some metadata. Let's print in here, print as this image tensor, and then \n image, and let's print another statement as image shape, the shape of the image, really important, as image.shape. We can access the shape using the shape property or the shape attribute, print f-string image data type. The data type is really important, image.dtype, image.dtype. 3 big issues in deep learning: image shape mismatches, data type mismatches, device mismatches. Image label as label, and then also print f-string label, data type as label, as type of label. Now this will print type of label, shape. So I think image.shape, no, we want to convert this image name into image in this way. Okay, we have to be careful about the naming. Now let's run that. We have image tensor as a tensor which represents the image. These are the image pixels, as you can see. These are the pixels, and also image shape, torch to size 3 channels, 64, and image data type is as torch.float32, which is the default data type for PyTorch. Image label as 0, and then label data type as class integer. So the type of the label is an integer. Okay, so this is some metadata about the image. The image shape is 3 channels, 64, the height, 64. Image data type as torch.float32, the preferred data type for models, and image label as 0, which refers to chocolate cake. And if we index on the class names and the index on the label, we will get the name as chocolate cake. So this is the mechanism of getting the class, the human readable way of the class. Now, if we wanted to visualize it, we can go rearrange the order of dimensions by going image permute equals image.permute. We have to, in order to visualize this image in a Matplotlib, we have to permute it by going 1, 2, 0, and then let's print out different shapes. Print original shape as image.shape. So the original image as image.shape, and then this will give us the shape as channels, height, width, and then print f-string image permute as image permute dot shape. Now there's a question: why do we have to permute our images? Well, because PyTorch prefers channels first. PyTorch always prefers channels to be first. So 3, 64, as in this, PyTorch always must deal with color channels first, but Matplotlib prefers the other way around, prefers the color channels to be last. So we have to permute our image and rearrange the order of the dimensions. Here we have height, width, color channels. So we want to put the color channels last, and then we can plot the image using plt.figure, fig size equals 10, 7, plt.imshow, let's image show as image permute, and then pass in 1, 2, 0, and then plt.axis. We can turn off the axis off, and then plt.title as class underscore names, and the index on the label. Font size, let's specify the font size to equal 14. Now let's run that. Permute, we have an error in here. Image permute, image, we have to specify this as image. So we have to rewrite this as image in this way. And also here, tensor object is not callable. We cannot call this tensor object. Yeah, I thought that this was a function, but not. This is not callable. Let's run that. Now we have this image. As you can see, original image, torch to size 3,64,64, color channels first, height, width. So we have color channels 3, red, green, blue, 64, 64, and then we have permuted the image to be compatible with Matplotlib. 64 the height, then 64 the width, then 3 color channels, height, width, color channels, and then we can also put in here semicolon to prevent that from verbosing. And now we have a image of chocolate cake, as you can see in here, visualized using Matplotlib. And notice it is pixelated. Why? Because we have resized the image. We have downsized the image into 64 by 64. So we have so it has a low resolution image. Now let's turn. Now this step is important. This is the last step in data preparation. Let's turn loaded images into data loaders. Well, data loaders are really important for PyTorch. You will see data loaders everywhere. So note that we have to go down now. Okay, in here, and write our data loaders from torch.utils.data. Let's import DataLoader, and then batch size equals 32. Let's define the batch size as 32 by going 32. Batch size is 32, and then let's create our train DataLoader equals the class DataLoader, DataLoader, and then pass in here dataset equals the train data, comma. Let's set the batch size equals to the batch size 32. In each batch we will have 32 images, so you can change this to whatever you want. Okay, comma, num workers, the number of workers equals 1, comma, shuffle. Do you want to shuffle it? Yes, true, we want to shuffle it. And then test DataLoader equals DataLoader. We will use the DataLoader class also here, DataLoader class or instance, DataLoader object, and then pass in dataset equals test data, comma, batch size. The batch size equals the batch size parameter, batch size, comma, shuffle equals, do you want to shuffle it? Equals false. Usually we don't shuffle the testing data. So usually we don't shuffle the testing data. We just shuffle the training data. So shuffle equals true for the trained data loader, but for the test data loader we will set shuffle as false, and then comma, num workers equals 1. Let's now visualize train data loader and test data loader. Also, you can play around with the numWorkers. It's a hyperparameter which you can set. You can also set it to numWorkers as num_workers equals os.cpu count. CPU count will gives you how many cores on the CPU that will use to load your data. So if you check os.cpu count, how many CPUs we have? In this case we have 12 CPU cores, because we are enabling our, if you check our NVIDIA SMI, now we have our NVIDIA L4, the CUDA version is 12.4, so now we have 12 CUDA or 12 CPU available GPUs, and we can use or leverage those by os.cpu count function, and then specify in here num workers as the num workers, or you can specify them as 0. The default value, if you search in here PyTorch DataLoader, the default value will be 0. As you can see in here, the default value for the DataLoader here, torch.utils.data.DataLoader, the default value for numWorkers equals 0. But we can set them to whatever you want. This, the higher the better. So the more the better. The more workers to load your data, the better and the faster your data will be loaded. Okay? So we have here DataLoaders ready to go. Let's run that. Now, train DataLoader. We have train DataLoader, which is a train, which is torch.utils.data.DataLoader class at this location. And also the same thing, we have a test data loader, and we can verify that by going torch.utils.data.DataLoader at this location. If we try to get a image batch, image batch, label batch equals next, so we want to use the next function, and then we want to iterate through the train data loader and then get a batch from the loaded images, and then let's print in here, print image shape as image batch dot shape. This will be batch size 32, color channels, 3 color channels we have, height, width, and then let's print in here label batch shape as label batch dot shape, and let's run that. Beautiful. Now we have a batch of 32 images. Inside each batch we have 32 images, 32 photos, 32 photographs, and each photograph has 3 color channels of size 64. So this is 32 is the batch size, 3 is the number of color channels, and the same here. How many labels do we have for each batch? If you visualize label batch, we have 32 labels. So you have 32 labels: 0 chocolate cake, 0 chocolate cake, 2 cupcake, 3 sushi, and so on. So we have these samples mixed up. Why do we have these samples mixed up or shuffled? Because we have set in here in the data loader that we want to shuffle the data loader. Yes, shuffle. So shuffle equals true. Whereas if we get the next batch of the testing data, which is test image batch, test label batch equals next, use the next function, iterate through the test data loader, and then get the test label batch. We will get them in order. Why? We have all of them in as chocolate cake. Why? Because we haven't shuffled our test data, which is a common practice. As we said in deep learning, a common practice, the best practice is you don't shuffle the test data. You don't have to shuffle the test data. So set shuffle equals false. Okay? So now we have data loaders ready to go, and also we can visualize some samples from these data loaders. We can go train, or we can go image batch, image train, or image batch, image underscore batch, or batch image, whatever we have named it. I think we've named it as image batch, img batch, and then we have a huge tensor of 32 images. We have a huge tensor of 32 images, and we can get the image at index 0. It will be this tensor, and we can permute it, we can permute this tensor 1, 2, comma 0, and it will be permuted as this. And then plt.imshow, let's show the image and turn off the axes, and let's show it. plt.show, it will show the image as you see. Okay, so this image is coming from the DataLoader, from the batched data, from the batched dataset. So now we have batchified our datasets. We can move on to the next step, which is building the model. So now, or before we build the model, we can define a function called display random images. So we can go define. Let's define a function called display random images, and this function will take from me a dataset as torch.utils.data.dataset, comma classes, the classes as a list of strings equals by default none, and then comma n as integer equals 10, comma display shape as boolean equals true. Okay, then comma it takes from me also seed as integer equals none. So this function takes from me dataset as torch.utils.data.dataset, torch.utils.data.dataset, comma classes as a list of strings. We can also from the Python's typing module, let's import list tuple dictionary. Okay, so we have this typing hints, and then n as integer equals 10. Display shape, if you want to display the shape boolean, whether you want to display it or no. In this case, the default value is true, and then seed integer equals none. Let's now, the first step is adjust. So adjust display if n is too high by going if n is greater than 10. Let's go n equals 10. Display shape underscore shape equals false, and then print for display purposes. So for the purposes of display purposes, n shouldn't be larger than 10, setting to 10 and removing shape display. Okay, so now if n is greater than 10, then n equals 10, set the display shape as false because the default value is true, set display shape equals to false, and then print for display purposes n shouldn't be larger than 10, setting to 10 and removing shape display. Then the next step is set the seed if the seed is set. If seed, then random.seed pass seed in simple step. Then the fourth step here, or the second step, set the seed. The third step now is get random sample indexes using the random sample idx variable. Random sample idx equals random.sample. So we want to sample from the range of length. Let's pass in the length, and then dataset, comma k equals n. So whatever the number of images we want to display. The fourth step is loop or set up plot plt.figure. Let's create a figure. Fig size should be large, 16,8. So this is a large figure. And then number 6, we have to loop through. Let's loop through. Now this step is 5. Loop through random indexes and plot them with Matplotlib by going for I, comma, tag image or tag sample in enumerate. We have to enumerate through the random sample idx, and then tag sample, comma, tag label equals, we have to unpack the dataset, then at index targ sample at index 0, comma dataset of targ sample at index 1. Okay, so here we are getting the image at index 0, the dataset as at index target sample at index 0 gives us the image, at index 1 gives us the label. Now let's adjust the sixth step is adjust tensor dimensions for plotting. So we have to go targ image adjust equals target sample dot permute. So I have to permute 1, 2, 0, and then we have color channels, comma height, comma width. We want to permute it into this shape, which is the height width color channels, and then let's plot the adjusted samples by going plt.subplot. Let's instantiate a subplot 1, n, I plus 1, and then let's go plt.imshow. Let's image show the target sample or the target image adjust. Then plt.axis. Let's turn off the axis by going plt axis off. Okay. Then the last step is let's check if classes. If you have past classes, let's set the title equals to f string class as classes, and then targ label. If display shape, let's then title equals title plus f string \n shape as target image adjust dot shape, and then let's go plt.title as title outside of the loop of the classes, outside of the if condition of the classes here. And now we can run that safely. So let's run that. Now we have created our function, which is display random images. This function will help us visualize a number of images, a random number of images each time we call it. So let's now call this function by going call the function and plot random images. Now let's call the function plot random, or it's called plot images here. As you can see, plot or display random images, display random images, and then pass in here dataset equals train underscore data, comma n equals 5. Let's show 5 images. Then classes equals class names. Let's pass in here the class names, comma seed equals none. And now let's run the cell. So 3, 2, 1, and wonderful. Now we have a random set of images displayed, as you can see, and every time you run this cell you will get a different set of images. Okay, so we have cupcakes, chocolate cake, macarons, and so on and so forth. We will move now into an exciting step, which is replicating Tiny VGG architecture from scratch. So we will build this model from scratch, which is Tiny VGG model. The Tiny VGG model is implemented in a great tool called CNN Explainer, and we will open this tool by going CNN Explainer. As you can see, the CNN Explainer tool will show us this architecture. This architecture, if we try to search in here Tiny VGG, you'll notice that it implements the Tiny VGG. So in Tiny VGG, the dot product operation uses a stride of 1 and so on. You can read through that. Okay, so what does this architecture is called? It's called a Tiny VGG. Okay, and you can read in here what is a convolution network, so on and so forth. In machine learning, a classifier assigns a class table to a data point. For example, an image classifier produces a class table, for example, bird or plane, for what objects exist within an image. And you can read through that. The first layer in a Tiny VGG model is we have a convolution layer. The convolution layer applies the mathematical operation convolution. Convolution applies a kernel or a filter over an image that is convolved over an image, and then we pass the output, the feature map of the convolution, into a ReLU layer. This ReLU layer, if we click on this cell, it will show us the convolution operation. As you can see, we have a kernel. This is called a kernel or a filter or a window that is being convolved over the image, and it's extracting the features, extracting the patterns from the image as it convolves over the image. If we try to click on one of these cells, it will show us a window here, as you can see, which is a great visualization of the convolution operation. We have a kernel of size 3 by 3, so this is called a kernel, a window, or a filter of size 3 by 3. So we have 3 rows by 3 columns, and then this window is being convolved or moved across the image. So we have to slide this filter across the image, and as the filter slid over the image, it multiplies its weights. So the kernel values are called weights. It multiplies the weights or the values of the kernel by the image pixels, and then it produces a scalar. As you can see, the result of a convolution operation is always a scalar, and then we have now a scalar, a scalar, a scalar. Each time we multiply the weights of the kernel by the image pixels, by the region covered by the filter, we get one scalar, and then we result in, or this operation results in a feature map of all the scalars that is resulted by the multiplication of the weights by the image pixels. Okay, then after this convolution layer, we have a ReLU layer. The ReLU layer applies an activation function, ReLU, which is maximum. If you search here, ReLU activation function, we have the ReLU function, as you can see in images. This is called a ReLU function. So ReLU converts every single negative number. Every negative number will be converted into 0, and then 0 will be 0, and any positive number will be as it is. So 1 will be as is, 1, 2 will be 2, 3 will map to 3. So here we have negative values converted into 0, and then any positive value from 0 and to positive infinity all gets mapped to itself. ReLU applies an activation function to the convolution operation, and ReLU helps us activate the activations, or activate the most important values by applying the function ReLU. So if you click on here, as you can see, we have ReLU activation. It's also a kernel. We have here a kernel or window that's being slid over the image, because when we do a ReLU operation or max pool operation over the image, we get also a max pool, we get also a kernel to apply on the image. This kernel is being slid over the image and then choosing the maximum value. As you can see, we have the max function between 0 and 0.38. Of course, the maximum is 0.38, and then we will choose the value, or we will output the value 0.38 because it is the maximum. If we go to regions that has negative values, for example, this feature map has some negative values here. As you can see, minus 0.46 is lower than 0, so we choose 0, and then 0 will mean nothing, so we have a white pixel, as you can see. Okay, so we are applying the ReLU activation. Notice that ReLU will not change the shape. ReLU function will not change the shape. The input is 62 by 62, and the output is the same. The output shape is the same. We have 62, the height of the feature map, by 62, the width of the feature map. Whereas the convolution operation, we have here the images are inputted to the model. When we input images to the model, we input them of this size, 64 by 64 by 3 channels. But the convolution operation here will change the shape Okay, when we click on this, it will change the shape from 64 by 64 into the shape 62 by 62. Why? Because if we didn't add padding, if we didn't consider the padding, the convolution will terminate or will remove the extra edges in here. Okay, so we'll get rid of the extra edge, and as we apply more convolutions, it will eat more from the image. Okay, it will get rid of the extra edge of the border of the image. After the ReLU layer, we apply another convolution layer. So the pattern here is convolution, ReLU, max pool. This is one block. And then we have another block, which is the same pattern, convolution, ReLU, max pool. And notice the activations in the second block are stronger and are clearer than the activations in the first block. Because why? Because the model, the earlier layers, the model learns the basic features like edges, like textures. But in the later layers, the model learns the context, the scene of the image, the whole objects. Okay, the model starts to recognize objects in the image. The max pool layer also, as you can see, it slides a kernel over the image, and then it chooses the maximum value from this 4 values. So we have a kernel. This time this kernel size is 2 by 2. We have 2 rows by 2 columns, and it chooses the maximum value. The most important thing in here is that max pooling will reduce the size of the input from 60 by 60 to 30 by 30, because when max pooling has a kernel size of 4, meaning we have 2 rows by 2 columns, and also the stride value is 2, then it will reduce the image shape or the image size to the half. So it halves it. It halves the image. It makes the height and width half the value. If we have 60 by 60, it will become 30 by 30. And as we apply more max pooling, it will do the same thing. Why do we need to apply max pooling? Well, max pooling operation is important for 2 main reasons. The first reason is that max pool layer reduces overfitting, and overfitting is a common problem that happens or that occurs in machine learning models, in all deep machine and deep learning models. Overfitting, when a model is performing well and performing really well on the training data, but can't generalize to new unseen data. So when you have a model that's performing really well on the training data, but can't generalize, or the model is not able to generalize and to recognize new unseen images, then the model is considered overfitting. So the max pooling helps reduce overfitting. But why max pooling helps us reduce overfitting? It's important to understand why, not just what the max pooling does. The max pooling does the pooling operation, which is reducing the size. But why do we have to implement it? We have to implement max pooling because max pooling reduces the over-reliance of the model on features. When the model becomes over-reliant on specific features, like for example the edges, the corners, then the model will not be able to generalize to new unseen data. So max pooling helps us reduce the over-reliance of the model. Secondly, max pooling also tries to increase the capability to compute, because it reduces the input size. And when you have less input size, then the model will be able to compute faster. So it helps us make the computations faster, and also helps the model converge faster, rather than not just waiting for the model to train for a long time. Okay, so now let's implement this architecture into our Colab environment. Let's start now a new section. I think we have reached now section. Yeah, let's start section 5. Let's start a new section. Section 5, building a computer vision model, specifically image classification model, replicating Tiny VGG architecture. Now let's construct this class. Let's start class. Let's instantiate a class, or let's define a class by using the keyword class, and then Tiny VGG. Let's name it Tiny VGG. This class will inherit from the nn.module. All PyTorch models, all PyTorch deep learning models should always subclass this class, module. If you search for it, torch.nn.module, you'll notice that the definition of this class in the documentation says that base, the module class, is considered the base class for all neural network modules. So every neural network model should inherit from the module class. This is the most important and the most significant class for all neural network modules. Every single model you build in PyTorch must inherit from the module class. Okay, so now we inherited from nn.module using this syntax, nn.module, and now let's write a doc string in here. We will build a model architecture, replicating or copying, let's say copying the Tiny VGG from CNN Explainer website. Okay, the first method we have to define is the init method. So let's go define def underscore init underscore, and then pass in self. We have to pass self because this is a method inside the class, and we have to provide it with the self to represent our object. Input shape. What is the input shape? So what is the shape of the data that's coming to the model, that's being inputted to the model? In this case, I'm going to make the type of this data. This data will be defined as integer. So we have to specify the input shape as integer. This is called a typing hint, the type hint. So the hint for the type. When you see this int, you know, this should be an integer. We have to pass in here an integer. For example, not a float. You can specify it as a float, but here I want to specify the type of this data will be passed or should be passed as integer. Comma, then we have hidden units. How many hidden units we have? Here in CNN Explainer, how many hidden units we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 different hidden units, also called filters. So in CNNs, in convolutional networks, we call the hidden unit a filter. So in other words, we can name this as filter. So we have 1 filter, 2 filters, 3 filters, and so on. Also, you could say we have 10 kernels. We have 10 different windows. So we apply on each image that's being inputted to the model, we apply 10 different kernels, 10 different filters. So here, this will be as integer, and then comma, output shape. What is the shape of the outputs will be also defined as integer. Then this function, this init method, underscore init, so we are initializing the class Tiny VGG, should return none. So we have to return none. Now inside the init method, let's go super.init. Why do you have to do this step? This step is considered really important. Why? Because always when you inherit from a class in Python, you should call the super class, which is now module. So hey, super, which is module. You have to call init inside your child init, Tiny VGG init. So we are calling all of the properties and methods of the parent module class. We are calling it inside the init of the child, which is Tiny VGG class, by going super parenthesis dot underscore init underscore. So we are calling the init method of the super module class inside the init of the Tiny VGG class. Important step. Now let's define the first convolution block. Let's go self.conv block1. Now we will build the first convolutional block by going conv block1 equals nn.sequential. Let's instantiate this block as a sequential model. So a sequential model is a model that goes through each layer in order. Okay, so we have to go through each layer in order. First convolution, then ReLU, convolution, ReLU. We have to go it specifically in order. So we have to specify the model as sequential to be in a sequential order. The first layer in here is called a conv layer, a convolution layer. So let's define now a convolution layer, nn.convolution2d. We have in PyTorch, if you search here, nn-conv2d, we have a layer called convolution2d. This layer is the most important building block in every single CNN architecture. So there's no any architecture called CNN without a convolution layer. Every CNN architecture should contain at least one convolution layer. So this is the most important layer in a CNN architecture. CNN, or also called as ConvNet. This layer, conv2d, is short for convolution 2D operation, or convolution two-dimensional operation, applies a 2D convolution over an input signal composed of several input planes. This definition is really important. So the class conv2d, this is a class, as you can see, a class in PyTorch. It applies a 2D convolution over an input signal, which is an image composed of several input planes, which is the number of channels. In this case, we have 3 channels. In the simplest case, the output value of the layer with input size n will be the batch size. We have specified it as 32. Then channels in, the number of channels inputted to the model. We have 3 channels, comma, height, the height of the image, comma, w, the width of the image, and output, and then the convolution will output the same number of images entered to the convolution operation. If you have entered, for example, 32 images, it will output 32 images. If we inputted 100 images, it will output 100 images. So the same in. And then channels in will become channels out. Height in will become height out. If you don't specify padding, it will reduce the height. And then W, it will be W out, the output to the width. Can be precisely described as this equation. This is the equation for the convolution layer. As you can see, it is a kind of mimicking the equation of the linear regression model. We have a bias, and then plus the sum of the weights multiplied by the input. So the input will be the image pixels, the pixel values of the image, multiplied by the kernel weights, the kernel's values, the values of the kernel, or the values of the filter, and then we take the sum of this multiplication operation and then add the bias to it. Okay? And then we have to specify these parameters as we call this function. We have to pass in channels, out channels, kernel size, stride, padding. So let's define these by going the in channels equals input shape. This parameter up here, input shape. So we have to specify it as input shape, comma, out channels. How many out channels do we want? Now we are inputting, then later we will create an instance of this Tiny VGG class. We will specify the input shape to be 3 because we have 3 kernel channels. So the number of in channels here will be 3. Okay? So in channels will be 3. Out channels will be as hidden units. And also later, when we create an instance of this class, we will specify the hidden units as 10. So we will have here 10. The number of kernels will be 10. But now we are making the things dynamic. So let's go hidden units, comma, kernel size equals, let's specify the kernel size as 3. You can go a tuple, you can pass in a tuple as 3,3, and also you can pass in an integer. But I like and I prefer to pass in a tuple of 3,3, comma, stride equals, and then stride. You have to specify the stride value. For example, in this case, I will make it 1, comma, padding equals 0. Now you may ask, what is the purpose of stride, padding, kernel size? Well, in CNN Explainer tool, we have a great tool to visualize these hyperparameters. Here we have a section called Understanding Hyperparameters. The input size, you can make it 5 or, for example, 7. Let's make it 7. So this is the input size. For example, in this case, the size of the image will be 7 by 7. We have 7 pixels height and 7 pixels width. The padding now is 0. Okay. when we apply a padding, notice that the output will be 6 by 6. Why? Because here we have kernel size of size 2. If we make the kernel size 1 and also make the stride as 1, the padding as 0, then we will have the same output size as the input. Then the output size will be the same as the input. But once we increase the kernel size by 1 degree, then the output will decrease. Why? Because now you are taking a region of 2 rows by 2 columns. And when you convolve or when you move across the image, now this whole region corresponds with this single value, okay? But before, when the kernel size was 1, this region corresponds with this region, and this region corresponds with this region. This region associates with this region, and so on, okay? So we infer that increasing the kernel size will decrease the output size. Increasing the kernel size will result in a output size decreased. I wonder what would happen if we keep the stride 1 but also let the padding go up. If we increase the padding by 1 degree, if we decrease the input size and then increase the padding, let's go the padding as, let's make the stride as 2 and then add padding. The kernel size must be more than 1 for the padding to work, okay? So we have to specify. Now we have a padding of 1. You can notice that when we have a stride of 1, okay, let's keep the stride as 1. Now we have kernel size as 2. We will move by 2 pixel. We will move by 1 pixel each time. So we are moving by 1 pixel, but we have padding. This padding will result in output size that is greater than or larger than the input size. Why? Because we are protecting the image pixels by using a padding. Let's make the input size as 6. Now we will have the input as 6, but the output 7 by 7. But what if we increase the stride by 1? Then the output will decrease to 4 by 4. Why? Because now we are stepping by 2 pixels. Stride refers to the jump size, to the how many steps do you want to take. Now we want to take 2 steps, so we will move by 2 steps. And also when we go down, we will move by 2 steps, okay? And in a logical way, that means this will produce an output size smaller than the input size, because we are taking more steps. If you make it 3 steps, now the output will be 3 by 3. So we infer that increasing the stride value will result in a decreased output size. If we decrease the stride, the output will get bigger. If we increase the stride, then the output will get smaller. The padding will protect our values, okay? So if we don't have padding now, and we are taking a stride of 2, now you can see we have output 3 by 3, half the input, okay? When we have a kernel size by 2 and stride by 2, then it will have the input. The same as we said in the max pool. Because we have a max pooling of a kernel size 2 by 2 and the stride is 2, then the output will have the input. Then we will have half the input as the output, okay? So let's now return back. So now in channels, input shape, how many in channels do you want to input? In this case, 3 channels. Data, we will replace this by 3. When we pass here 3, then it will gets here 3. The hidden units as 10, because we have 10 hidden units. And then also the kernel size, I have specified it as 3 by 3. You can experiment. Feel free to experiment. You can try 5 by 5. You can try 7 by 7. Or you could go crazy. You can try 10 by 10. Okay? Or also you can try a small kernel size 1 by 1 and make an experiment for this one, and for this one, and then choose the best model. Always experiment to try the best model, to know which model or which hyperparameter values will give you the best results, will result in the best results. Stride, you can try stride to be as 2. Okay? They say that the stride rarely can be more than 2. So we rarely see that someone is setting the stride to a value more than 2. Okay, padding, you can specify it as 0, valid, which is valid, meaning no padding. The output will be the same as the output will be smaller than the input. And you can try 1. 1 will result in a padding that will protect, that will give us the same output size as the input. And also you can try a padding of 2. 2 will give you a output shape greater than the input shape. Okay, so this is the first convolution layer. It will perform a mathematical operation over the images, which is the convolution layer. We will initialize, don't forget, now we are not doing transfer learning. Now we are doing building a model from scratch. So the kernel's weights will be initialized randomly. The kernel's weights will be randomly. And then when we train the model, the back propagation algorithm and also the gradient descent algorithm will try to optimize the weights inside this kernel to better represent our data, to better understand the objects inside our images. Stride value will also define the jump size, and padding will whether we want a padding or no. In this case, I'm setting it to 0. That means I don't want padding. Then the next layer, as we have in this architecture, the next layer after the convolution will be a ReLU layer. So let's add now a ReLU layer by going nn.relu, nn.relu, a ReLU layer. As we said, ReLU is an activation function. This activation function will choose the maximum value between the pixel value and the 0. For example, this pixel, now we have 0.47 and it is the maximum over the 0. So we choose 0.47. What is the purpose of ReLU? Why are we implementing ReLU? ReLU helps us to learn complex nonlinear relationships. So ReLU layer adds the complexity to the model. If you want your model to learn complex nonlinear relationships, you have to use ReLU. ReLU adds complexity to the model, and also it allows the model to learn nonlinear relationships. So curved relationships, okay? Relationships. Then we will add another convolution layer by going NN. So the NN module in PyTorch helps. NN module contains most of the popular layers in deep learning. It contains convolution, it contains linear layers. You can visit that by going torch.nn and see the NN module. So NN is a sub package inside PyTorch. It's a sub library that contains, these are the basic building blocks for graphs. Graphs is another word for networks. We have convolution layers, pooling layers, padding layers, nonlinear activations. We have normalization layers, recurrent layers, transformer layers, dropout layers, and we have a whole bunch of different building blocks, all that helps us build really large networks. So every single layer you can imagine, you can find it inside torch.nn. After this ReLU, we will apply a convolution layer by going nn.conv2d. So we write conv2d. Note that the d is small, not as in TensorFlow. TensorFlow uses a capital D, but here we use a small d. Then pass in channels as hidden units, comma, out channels. The number of out channels will be hidden units. Why? Because this layer will receive the inputs from this ReLU layer, and the ReLU layer will output 10 hidden units, because we are getting out channels from here as 10. Okay, so when you output here 100 units, you have to receive here 100 units. This has to match. The output of the previous layer has to match with the input of the next layer. This is the feed-forward fashion in deep learning. Then the out channels will be hidden units, which is of course 10 in this case. The kernel size, let's set the kernel size as 3 by 3. So you have 3 rows by 3 columns, comma, stride equals 1, comma, padding equals 0. We don't want to apply any padding. Okay, Then after this convolution layer, we have another ReLU layer. If you refer back to the architecture, we have convolution ReLU. The ReLU will learn complex, nonlinear relationships inside data. Will help us add complexity to the model, or also it adds the ability to learn complex patterns. Then after this ReLU layer, we have a max pool layer. So let's go nn.maxpool 2D. So this is a maximum pooling layer. Max pool, as we said, it's an important operation in CNNs or in a convolution network. Every convolution network contains a combination of convolution layers, ReLU layers, and max pool layers. So most of these CNN architectures contains a combination of convolution layers, ReLU layers, convolution layers, followed by ReLU layers, followed by max pool layers. The max pool layer receives from me, if I search in here, always look up the documentation, max pool 2D layer. Max pool 2D, this is a layer inside PyTorch, applies a 2D max pooling over an input signal composed of several input planes. As we said, if we choose, for example, this image for max pooling, then if I hover over this region, it will choose the maximum value from this window. Now we are hovering a window of 2 rows by 2 columns. So we get here 2 rows by 2 columns. This is the window size. Then the max pool layer will apply a max function, choose the maximum value, choose the most largest value from this window, which is now 2.71, and outputting it to the next feature map. And by doing this, it halves the input from 60 by 60 to 30 by 30. Okay, as we said, this helps us reduce everything. So let's go kernel size. Let's specify the kernel size as the same in here. We have the kernel size here as 2 by 2. So let's go here, kernel size equals 2 by 2, comma, the stride will be as 2 by 2. Default stride value is same as kernel size. The max pool layer will help us in solving 2 things. Let's write it in here. Max pool helps us reduce everything by reducing the over reliance of the model on specific features, and also max pool helps us make the processing and computing faster inside the convolution network. Now congratulations, we have built the first convolution block, which is conv block 1. Let's now build the second conv block by going self.convolution block 2. This time our rhythm will be faster because we have explained the necessary information. This sequential block will contain a convolution layer, conv2D layer. This conv2D layer will receive in channels as hidden units. It must receive the in channels as hidden units because we are outputting here the number of channels. The out channels will be hidden units. So this layer must receive the same number of channels or the same number of hidden units, comma, out channels equals hidden units, comma, kernel size. So the size of the kernel, the size of the filter, what is the size, how many rows, how many columns? Let's make it 3. Let's use now one integer to practice different syntaxes, comma, stride equals, let's set it as 1, comma, padding should be 0, or padding must be 0. After this convolution layer, let's add a ReLU layer. The ReLU will help us learn complex patterns. Then nn.conv2d, another convolution layer. In channels should be as hidden units, comma, out channels equals hidden units, comma, kernel size, the kernel size, so the size of the window, the size of the filter should be 3, comma, stride, how many pixels do you want to jump over? How many pixels do you want to move across? 1, comma, padding. Do you want padding? If you want padding, set as 1. I don't want, so I will set it as 0. Then let's add another ReLU layer. Lastly, we will have a max pool layer. Dot max pool 2D layer, and set the kernel size the same as the explainer here. we have a 2 by 2 kernel size. You can see here we have 2 rows by 2 columns. So let's replicate that. Kernel size equals 2, and the stride must match the kernel size for the max pool by going equals 2. The last block we will build is the classifier block. If you notice in here, this is the second block in here. Okay, so we have, this is the first convolution block, which is convolution ReLU conv ReLU max pool. Then we have a second block here, conv ReLU max pool. After this max pooling, which is this one, we have here an output called a layer. We have a layer called output. But if you click on this in here, it will show us a hidden layer called flatten. So we have to flatten the feature maps that's being outputted from this conv block 2. The conv block 2 will output a feature map. The feature map is a matrix, which is of this size, okay? Of this size, 13, the height, 13, the width, and the number of channels, 10. So we have to flatten the shape to be able to pass it to a linear layer. Okay, so we click on this, and then it will show us a flatten layer that will flatten the matrix into a vector, into a feature vector that contains 1690 values. Now let's go ahead and create that block by going self.classifier equals nn.sequential. Let's define a sequential model. This sequential will have a flatten layer that will help us. So this flattens the feature map matrix into a feature vector, which is of 1D dimensional. Why? To be able to pass it to the linear layer, and classify. Okay, so after this flatten, we have to specify one linear layer to classify, nn.linear, and this linear layer will have the number of in features equals something, comma, out features equals something. Now, as a question, what is the in features will be? Well, the in features will be the same size of this matrix, but flattened. So when we multiply 13 by 13 by 10, we will have here, if we try to multiply 13 by 13 by 10, then you will get 1690, the same number that's in here. If you click on this, the flatten layer will output a feature vector, a vector of this size, 1690, because it flattens this matrix. This is a matrix that contains height, width, and then kernel channels 10. The flatten will flatten it into a long feature vector that contains all these values. If you have over it, it contains all these values, but not in 2-dimensional, in a 1-dimensional way. So it collapses the matrix into a vector. So we have to specify in here as 13 by 13 by 10, and the output features will be output shape, which is the number of classes that we have. You can do like this: hidden units equals hidden units times 13 times 13. The same syntax, just using the variable hidden units. Now, after defining the blocks that we need in our CNN model, let's build our forward pass by defining another method outside of this init method. So note the line here. We have this line outside of the init method for the same indentation like this. We want to create a forward method. So the same position here. Def forward. You have to be careful about the indentation spaces. Let's define a method called forward. This method is a must because it will specify the forward computation of the model. We have to pass in self because it's a method, and then comma x. Now x will equal self.convolution block 1, and then we will pass x through the first convolution block. Then x equals self.convolution block 2, we will pass the output of the first convolution block as the input to the second convolution block, x, and then the output of the convolution block 2, we will pass it as an input to self.classifier, and then pass here the x. Okay, so this syntax will do the same like this. If you return x here, now let's try to print x.shape in here, and then after the second convolution block, let's print in here x.shape. After the classifier, let's print also the x.shape, because I want to visualize the shapes. Now if you run this model, perhaps you forgot a comma. Yes, of course, we have forgotten a comma between the flatten and the second linear layer. Now let's run it again, 3, 2, 1, and congratulations, now we have built our model successfully. Let's instantiate our model by going, let's get rid of this. Let's instantiate a model, which is instantiating a new instance of the Tiny VGG model. Let's set the seed by going to torch.manual seed, and then specify it as 42, and then let's go model equals Tiny VGG, and then pass in. We have to pass in the same parameters that we have specified earlier. We have to specify input shape, as well as hidden units, as well as output shape. So we have to pass in how many in channels we have, how many hidden units do you want, and also the output shape. Now let's pass these values. Of course, the input shape will be as, if we visualize one image, we have image. Okay, let's convert it into a data transform using this data transform. It will result in a tensor. Now what is the shape of the tensor? You have always, as a machine learning engineer, as a deep learning engineer, you have to know the input shapes and the output shapes. Why? Because models will require a specific input shape, and also will require a specific output shape. So what is the shape of this image? Well, it has 3 color channels, and the height is 64, the width is 64. The input shape here requires from me how many channels do you have, because I will pass this parameter. Note that this is an important point. I will pass the value of this parameter to the parameter of the convolution layer in here. The in channels will be the same as input shape. So how many in channels do you have? If you read in here, what is the definition of in channels? Number of channels in the input image. So there are 2 possible values, 1 or 3. If you have grayscale images, for example, this grayscale images, this is a grayscale image. So grayscale images have just 1 value. Okay, so grayscale images have just 1 value, 1 channel. Whereas color images like our images are now color images. If you visualize our image here, let's visualize it in here. Our image is color image. It has colors. It has red, green, blue color system. So we have to pass here as 3. So number of color channels in the images, in our image data. Then we have to pass in the hidden units. How many hidden units do we have? Well, I told you this is a hyperparameter. You can specify it as 100, as 64, as 32. Always we prefer the multiples of 8. So if you want to specify how many filters, it could be as, for example, 8, 16 units, or 64, or also 128. You can specify that. But in this case, we are replicating Tiny VGG. How many hidden units do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 hidden channels, 10 hidden units, 10 filters. So we will apply on every single image that's being inputted to the model, we apply 10 different filters, 10 different kernels. Each kernel will learn a feature. Each kernel will learn a pattern. Out features, how many out features do we want? Well, how many class names do we have? How many classes do we have? We have 4 classes: chocolate cake, cupcakes, macarons, and sushi. So if you try to get the length of it, will be 4. So we have to pass the same number of classes that we want to classify into as in here by giving length of class names, and then .to device. .to, let's move into the device that we have specified earlier. We have the device as CUDA. So we want to move the model. We want to transfer the model to the target device, which is CUDA. Now we have built our model instance. Model equals Tiny VGG and defined the values as you can see. Let's now display our model architecture by going model. Now we have this architecture as displayed. We have convolution block 1, which is a sequential model containing the following layers: convolution layer, ReLU layer, conv layer, ReLU layer, max pool, total of 5 layers, and then conv block 2, also total of 5 layers. Start counting from 0 because we are dealing with Python as a language starts counting from 0, and also the classifier has 2 layers, flatten layer and a linear layer. Let's now try to do a test forward pass. So try a forward pass. We have now 4 or 5.1. Try a dummy forward pass, by passing a single image. Okay, and now we have to get a single image batch by going get a single image batch and label batch. You can get the label batch also by going image batch and comma label batch label underscore batch equals the function next to get the next batch, and the iterate through the train data loader that we have created previously. If you show now image batch dot shape comma label batch dot shape, it will print the following results. We have a batch containing 32 images. So every single batch contains 32 images. We have specified that earlier. Recall, this is a hyperparameter. You can fine tune it. You can experiment with different values and see which value results in the best results. Comma, 3 color channels. Each image has 3 color channels, red, green, blue, of height 64, of width 64. So if you want to visualize this image batch, it will be a huge tensor, a magnificent tensor containing all of these images. So you can see we have a large magnificent tensor containing different images. Okay, we have a tensor of values here, then tensor second image, this is a third image, then the dot, this means we have more images but not being showed here for display purposes, and here we have image tensor, and as you can see, this is a huge tensor containing of 32 images. This tensor has, if you check the shape, it has 32 images of 3 color channels of 64 by 64. And also we have label batch. The label batch, we have a tensor of 32 labels. Now let's try to do a dummy forward pass to check the model. It's good practice. It is considered to be a good practice to pass a dummy forward pass through the model to check whether the model works or not, whether the shapes are correct or not. Let's do that by going try a forward pass. Let's now try a forward pass. We have our model, and then pass in our image batch, and we have to move. If you run this like this, let me show you that. If you run this cell, we will get an error. Which is of type runtime error. So the type of this error is runtime error. Input type, so the data type of the input is torch.floatTensor, and weight type torch.CUDA.floatTensor should be the same, or input should be a mkldnn tensor and weight is a dense tensor. I wonder what is the cause behind this error. Well, let's check the device of each of our image batch and the model. So now we have a model. This model, I think we have moved it to the CUDA device by using this syntax, .to device. So we have moved the model. We have transferred our model to the target device, which is device CUDA. So in order to make predictions or do a forward pass with image batch, the image batch must exist in the same location or in the same position as the model. So if you do image batch, we have a long tensor. As we said, it's a huge tensor of 32 images. If we check the device of it by going to device, this image batch lives on the CPU, which is considered device mismatch, because the model is on the GPU CUDA, but the image batch is on the CPU. So we have to move the image batch to the GPU, to the CUDA GPU, by going .to device. So now we are moving the image batch. We are putting the image batch to the target device. And now, as you can see, it made those predictions correctly because we don't have any mismatches. Now we have a huge sensor here of predictions. Each image gets a one row because we have inputted 32 images. If you check the shape of image batch, we have image batch, a huge sensor of images. If we check the shape of it, we have 32 images. So the model will make 32 predictions. So the model will make 32 predictions. For each image, there's one prediction. And if we try to now make the image batch at index 0, try to get the first batch by going at index 0, and then to unsqueeze, we have to unsqueeze it. We will get just a single prediction. As you can see, we have just one single prediction for one single image. Okay? These are called logits. The logits refer to the raw scores that is being outputted from the model. So the model outputs raw logits. The logits are raw scores that represent how much the model thinks that this image belongs to a specific class. And notice that the tensor of the logits are living on the CUDA device, on the CUDA GPU device. If we try to get it the same as before, we have 32 images. Let's get rid of this because we want all the images. Now we have, as before, 32 predictions or 32 logits. The output shapes that we have printed earlier here in the food method, remember that we have printed the shape after the first conv block and also printed the shape of the second conv block and also printed the shape after the classify layer. Now let's check the shapes. If we go down to the forward pass that we did earlier, note that we have here 3 different printouts. If we specify, if we store this inside a variable called logits, then it will show us just these outputs. Okay, now I want you to focus here. What is the output shape after the first convolution block? What is the output shape after the first block here? Well, the output shape is 30 by 30 by 10, which is the same in here. We have 32 images. Each image is 10 channels here, 10 channels, and then we have 30 the height and the width. So I have here 30 by 30. So the same output shape after the first convolution layer. As I told you, you can specify this as 0 and then .unsqueeze to get just the first image, not all 32 images. Now if we run that, we have here one image, and also you can squeeze that. Okay, but there is no need for that. I want to make sure that the output shapes are lining up. So we have here 30 by 30 by 10, the same as here, 30 by 30 by 10. But PyTorch prefers channels first. PyTorch library prefers the channels to be first. So here in the CNN explainer we have channels last. But in the PyTorch library it prefers channels first to be first before height and before width. And what is the output shape after the second conv block? Well, it is 13 by 13 by 10, and here we have 13 by 13 by 10, the same output shape, which is really great. And then after the flattened layer, what is the output shape here? 1690. We have here for each, when we pass through, if we print in here the shape of this, 1 times 10 times 13 times 13, the same numbers in here. If you multiply them, we will get this number, 1690. And then the model will produce for each feature vector, will map this feature vector into 4 probabilities, into 4 logits, okay, to classify into 4 different classes: chocolate cake, sushi, macarons, and also cupcakes. Okay, so this is an explanation of the model shapes. It's important always to consider the input and output shapes in machine learning projects. Let's now comment the print out, which is the print function, because this will be party. Then when we train the model, it will verbose the training page with the print outs. So we have to comment the print statements, not the convolution blocks calls. And now let's run these cells again to make sure that it works, and it worked, all of them. As you can see, it didn't print the output shapes. Let's now visualize the logits. These are the logits. We have 32 logits. For every single image, we have one vector. So for each image, we have 32 images. Now we are predicting on a whole batch. So the model is producing 32 logits or 32 outputs. This is for one image. These logits are for one image. These logits are mapped for one image, and so on and so forth. So we have logits corresponding to the number of images. And note that these logits are existing on the CUDA device. On the CUDA device, device equals CUDA at index 0. And why do we have 0? Because this is the first CUDA device. Now let's build a try block, or let's put a title in here as 5.2. Use torchinfo to get an idea of the shapes going through the model. So torchinfo is a package or a library that helps us visualize the architecture of the model in a more detailed way. So let's go try, and then we will try to import the library torchinfo. As we said, torchinfo is a library that helps us visualize the architecture layer by layer, step by step, using a function called summary. Except if we don't have this library, then let's pip install torchinfo. Let's go ahead and install the torchinfo library, or install the torchinfo package. And also we have to import torchinfo. And also you can use the flag q to install torchinfo quietly by going install -q. You can put -q to install it in a quiet mode quietly. Let's now run that, and now it is installing torchinfo. So it tried, the Python language tried to import torchinfo, and it wasn't able to import it because we don't have access to torchinfo until we install it. Then it came to here, except block, and then pip install quietly the torchinfo package, and then import torchinfo, and it imported it correctly. And as you can see, we have a check mark in here. Now we have access to torchinfo. Let's now go from torchinfo, import summary. And now we can use this function. It's a simple function, and pass in the model equals our model, comma, the input size. So what is the input size? This is an example of the input image shape. So what is the shape of the image? You have to pass in an example batch of the input shape. So let's pretend that we have a batch of 1, so every batch contains 1 image, comma, we have 3 color channels, comma, 64, comma, 64. So you can pass in here a list, or you can pass a tuple. Whichever object you prefer, you could use. I will pass it as a list of batch size. So here the n is a batch size. How many samples do you want? You can make it 100, you can make it 32, whatever you want. I want it for an example of 1 image. And then number of color channels, it must indicate, this must indicate how many channels do you have. In this case we have 3 channels, red, green, blue, and then 64 by 64, the height and width. Now let's run this function, and it printed out a summary of our model. So layer, we have layers, Tiny VGG. We have a model called Tiny VGG, which consists of, this model consists of 3 sequential blocks. Sequential 1-1, sequential 1-2, and then sequential 1-3. The first sequential block contains these layers: convolution, ReLU, convolution 2D, ReLU, max pool. And the second block contains conv, ReLU. You can see these are children to the sequential block. They are coming from the sequential block parent, ReLU, convolution, ReLU, max pool. And then inside the third sequential block, we have a flattened layer and a linear layer. And here we have output shape. So the output shapes of each layer. The Tiny VGG model as a whole architecture, this architecture as a whole will predict the number of classes. Here we have Tiny VGG. For each image, it will produce 4 logits. So if we pass an image through the Tiny VGG model, it will produce a tensor of shape 4. Let's now verify that by getting a single image. Let's get a single image. For example, from the image batch, let's get the first image. This is a sample image tensor. Let's pass this tensor, let's pass it through the model. But first we have to check the shape. It has 3 channels, 64, 64. To be able to pass this image as a single image to the model, you have to unsqueeze it. You have to unsqueeze it to add an external dimension, which is the batch dimension at index 0. So you can pass dimension equals 0. Now we have this tensor, and if we check the shape of it, we have 1 by 3 by 64 by 64. So we added in an extra batch dimension. This is necessary and required to be able to pass this image to the model. Now if you pass it to the model and move it to the device, we will get a tensor of 4 outputs. So we have a tensor of 1, 2, 3, 4. So for each image, for every single image, the model will produce 4 logits, 4 outputs. As you can see in here, we have 1, 2, 3, 4 logits, 4 probabilities. So this is the output shape after the whole layer, after the whole model. But the output shape after the first sequential block will be 1, 10, 30, 30, which is the same as this 1, 30. So one image, 30, 30, 10. The same in here. We have 30, 30, 10, and then we have the shape after the first convolution layer. This shape is after the first sequential block as a whole, but this output shape is after the shape after the first convolution layer, which is 1, 10, 62, 62, because we are inputting images. Remember, the images sizes are 64, 64, 3, and the convolution has no padding, so it will reduce the size, the height and width. So it became from 64, it became now 62, 62, 10. So the same here, we have 62, 62, 10, and remember, we have here color channels last, but PyTorch prefers channels first. And here ReLU will be the same size, 1, 10, 62, 62. ReLU layer will not manipulate the image shape or the shape of the tensor. Then we have another convolution layer with no padding. Well, because we don't have padding, it will reduce the height by 2 pixels and reduce the width by 2 pixels. Then we have another ReLU layer, which is 1, 10, 60, 60. The same shape with no any manipulation, with no any changes, because ReLU doesn't change the shape. Then we have a max pool layer, which reduces the image size to the half. Now if you look in here, 1, 10, 30, 30, because the half of 60 is 30. And you can continue with that, following along with the shapes of the architecture. But here, after the flatten layer, we have 1,1690. This is the feature vector size, the size of the feature vector that contains the compressed version of the image in a vector format. Flatten layer will help us to flatten the image matrix, to flatten the feature map, to collapse it into a 1D vector, to be able to pass it, or to allow us to pass it to the next layer, which is linear layer, because linear layers, unlike conv layers, deal with data in 1D, in one-dimensional way, but convolutions deal with data in a 2-dimensional height and width. Linear deals with vectors, and then this linear layer will map this number of neurons into just 4 outputs, 4 logits. And then we have important information here. The number of total parameters, we have 9,774 parameters as the total number of parameters inside the model. The trainable parameters are, all of these parameters are trainable, 9,774. All of these parameters are trainable, meaning they could be adjusted or modified using the gradient descent algorithm. Non-trainable parameters 0, and then the total multiplication, additions, operations in megabytes of this new torque, we have 5.69 total size or storage for all of the multiplications happening inside these layers and the additions happening in these layers. So the total multiplication dash additions in units using the megabytes, we have 5.69. And what is the input size? The input size of the image, so every single image will be 0.05 megabyte. So every single image sensor will be stored in a 0.05 megabyte, every single image. The forward and backward pass size is 0.71. So the forward pass and the backward pass will take from the memory, or will occupy 0.71 from the memory. Parameter size, so what is the parameter size? We have 0.04, the parameter size. Here we have 9,774 parameters, and these parameters could be stored in a file of this storage, 0.05 megabyte. Note that we have here megabytes. In the future, when you deal with harder models, you will deal with models with millions or even billions of parameters. And here, you will have the storage unit as gigabytes. For example, ChatGPT has 1 trillion parameters. And I think this amount of parameters will not be able to fit into megabytes. It will fit into gigabytes, into hundreds of gigabytes. Estimated total size as 0.80. So estimated the total size of the model, including the input size, the total multiplication additions, including the parameter size, will be 0.8 megabytes. This is the estimated total size. So torchinfo is a great library that will help us visualize the architecture and also some important metadata about the model. Let's now construct a training loop to train our model. So let's go ahead and section 6, creating a training loop and testing loop to train and evaluate our model. Well, we will functionize it to be easier to call the functions. So now let's create a function. Let's define a function called train step. This function will do a single training step, and it will take from me the model which model do you want to train. So you have to pass in the model object that you want to train as torch.nn.module instance. So this model will be of type module, will be of this type, or this model will inherit from the module, must inherit from the module class, comma, DataLoader. So which DataLoader you want to use to train the model on. So which dataset you want to train the model on will be as torch.utils.data.dataloader, and then we have to pass in the loss function to calculate the loss function, which is as torch.nn.module, comma, we have to optimize our weights using an optimizer. So let's go optimizer as torch.optim.optimizer, and then comma, the device will be as equals device. And now let's specify a docstring in here. This function will train a model on the DataLoader and optimizes the model's parameters. Okay, so this is a short description of what this function does. This function will train a model, whichever model you pass in here, on the DataLoader, also whichever DataLoader you pass in here, and optimizes the model's parameters to better, let's put that after this line, the model's parameters to better represent our data. And let's put this down here, and optimizes the model's parameters, and let's raise that to here like this. Now let's do the steps in here. The steps are easy. The first step is we have to put model in train mode by going model.train. So now we are setting the mode, or the mode of the model into training mode by going model.train function, and then we have to set up train loss and train accuracy value by going train loss. We have to set up train loss, train underscore loss, comma, train accuracy equals 0, 0. So we have to initialize the train loss and the train accuracy to 0, 0. We have to initialize or start the loss of the training as 0, start the loss of the training as 0, and also start the accuracy of the training as 0. Then the next step is loop through. We have to loop through DataLoader and data batches. Let's loop through DataLoader data batches by going for, let's construct a for loop for batch, comma, x, comma, y. X will be a tensor of images, and y will be a tensor of labels, of truth labels. In enumerate, we have to loop through the DataLoader that we pass in here, the DataLoader. And then we have to send data to the target device, by going x, comma, y equals x dot to device. So we have to move the x to the target device. We have to transfer x, this image tensor, into the device by going dot to device. So we have to move x to the target device, comma, y dot to device. So in order to compute on these tensors with the model, because the model lives on the CUDA GPU device, we have to move the x and y tensors into the GPU by going x.to device, comma, y.to device. Send data to the target device. The first step of the training will be as fourth step. So we have, first of all, we have to pass the images, pass the photos, pass the pictures through the Tiny VGG architecture. Then the Tiny VGG will start with random weights, will start with crazy weights. It will produce crazy outputs, crazy logits. Then after the fourth pass, we will calculate the loss. So first of all, we will do a fourth pass. We will go through each of the layers and produce outputs by going x prediction equals model, and then pass in the tensor of the images. This tensor will contain 32 images, 32 photos. Pass this tensor that is consisting of 32 images, pass it through the model, and then the model will produce like this, produce 32 logits. Okay, 32 logits. And by the way, these logits are now crazy because the model isn't trained yet. If you try to get the argmax at dimension 1, all of the predictions are 2, so they are random. The model is performing as good as random. The model is random. It is guessing. So all the model predicted all the images in this batch, predicted it as 2. Okay? So now we will train the model and make the model better. Now after the forward pass, after doing the forward pass, we have to calculate loss. Calculate the loss by going loss equals loss fn. We will use loss function and then pass in here ypred comma y. So we are comparing the y or the x. Here we have to call it ypred. So we have to call here ypred. So we are comparing the y predictions, comparing it to the truth labels, and calculating the loss function. The loss will be cross entropy. Train loss equals loss dot item. So we have to get the item version of the loss, and then plus equals, we have to add it accumulatively, add it to the train loss. So we have to accumulate the train loss each time. So for each batch, we have to accumulate the loss item, accumulate it or add it accumulatively to the train loss. The train loss here is starting as 0, so we have to add the loss each time. The third step is optimizer, 0 grad. We have to zero the gradients of the optimizer by going optimizer dot 0 grad. Important step, 0 gradient. The fourth step is we have to apply back propagation algorithm by going loss dot backward. So we are calling the backward function on the loss that we are computing in here. So loss dot backward to perform back propagation algorithm. The back propagation will calculate the gradients of the model's parameters or with respect of the model parameters in terms of the loss value. If the loss value is high, the back propagation will calculate really influencing gradients to influence the weights, to force the optimizer to update the weights. And then the fifth step is here hash 5. We have to optimize the step. We have to perform the optimization using the gradient descent algorithm. So this step will perform the gradient descent algorithm. So we have to go algorithm. We have to go optimizer.step. Optimizer.step. This step will improve the weights of the model. So to improve the weights and biases of the model. Then we have to calculate here. If we return back after this step, we have to calculate accuracy metric ypred class equals torch.argmax. We have to get the argmax of torch.softmax. So we have to apply the softmax function over the logits here. The model here will output outputs raw scores, raw logits, and then we have to convert these logits, which is ypred, pass it to the to the softmax function at dimension 1, and also get the argmax at dimension equals 1. Train accuracy, let's accumulate it, plus equals accumulate the ypred class. If it equals y, then get the sum, get the item dot item method, and then divide it by the length of ypred. So here we are in these two lines, we are calculating the accuracy of the model because we don't have a built-in function to compute the accuracy in PyTorch. And then we have to adjust the last section in training. We have to adjust metrics to get average loss and accuracy per batch by going train loss equals train loss, and then divide the train loss by the length of DataLoader, and also train accuracy equals train accuracy, divide it by the length of DataLoader, and then lastly we have to return train loss and train accuracy. And the train loss, train accuracy, we have initialized them here to be zeros. As you can see, we have initialized train loss and train accuracy to 0, 0, and then for each batch, we are looping here for each batch. For each batch, we are doing a forward pass, calculating the loss, and then accumulating the loss for each batch, accumulating it on the train loss variable. And also here, we have accuracy. We are accumulating the accuracy for every time for each batch, accumulating it for the train accuracy. Now let's run that function. So now we have created a function of train step that will train our model. Now we have to create another function to test and evaluate our model. So let's go define test underscore step. This function will take from me a model as torch.nn.module. So the model will be passed of this type, torch.nn.module, because as we said, models always inherits from the module class, comma, DataLoader as torch.utils.data.DataLoader. The DataLoader class is an efficient DataLoader that stores our images inside batches. So we have to test the model on a DataLoader, on the test DataLoader. If we print in here test DataLoader, we have this test DataLoader. So we want to evaluate our model, test our model on this test DataLoader, okay? And after this DataLoader, we also need to calculate the loss function as torch.nn.module, comma, device should equal to device that we have already set up. Now we have to, first of all, put model in eval mode. So as in the train step function, we put our model in train mode. So here, notice, put model in train mode, model.train. This was in the train step function. The same step we have to do in our test step function. So let's go model.eval to set the module in evaluation mode. Then let's before turning on the inference mode, let's set up the test loss and test accuracy values. So test underscore loss, comma, test accuracy, test underscore ag equals 0, 0. So we have to initialize our variables test loss, comma, test accuracy by 0, 0. So the test loss will start 0 and also the accuracy will start at 0. Then we have to turn on inference mode. Turn on inference mode by going with torch. So with context manager. With is a context manager in the Python programming language with torch.inference underscore mode. So this function will enable us to turn on the inference mode and turn off the backpropagation gradient descent process. Now let's loop through DataLoader batches by going for batch. So for each batch, comma, x, comma, y. So the x will store a batch of images and y will store a batch of labels. In enumerate, let's loop through the DataLoader that we have to pass into here, the DataLoader. Send data to the target device by using this syntax x, comma, y. Let's use x.toDevice. Let's send x to the target device. Also the y, we have to send it to the target device. So note the same step we did in the train step. Here in the train step, we set up train loss and train accuracy values. We have initialized the train loss to start at 0 and the train accuracy to start at 0, and then we looped through the DataLoader data batches by going for batch, comma, x, comma, y in enumerate DataLoader, and then we have sent the data to the target device to make it compatible with the model. And then we have to do the steps of the testing as we did here. These are the steps of training, but now the steps will differ because now we want to test the model. So the first step will be forward pass. So as in training, also in testing, while testing, in order to test the model, we have to do a forward pass. So test underscore pred underscore test pred underscore logits. So the test prediction logits equals model, and then pass in the x. X is a tensor of images, so the model will predict on the images, will pass the images through the architecture, through the conv layers, through the ReLU layers, the max pool layers, and then will produce outputs, logits, and then store these logits inside this variable. Then the second step is calculate the loss, and the loss, as we did in the train step, loss equals loss function, and then pass in here test underscore pred underscore logits, and compare these logits by the y. Y is a tensor that stores the truth, the ground truth labels, the ground truth targets, the ground truth outputs, and comparing them with the logits that the model produces. So we want to evaluate the quality of the model. Test underscore loss, we have to accumulate the loss by using this syntax, plus equals, and then going loss.item. So the same step we did in here in the train step, function. We did a forward pass by applying the model on the images, and then the model will produce logits. The second step is calculate the loss by using the loss function, and then calculating the difference between the y-pred and the truth labels here, storing them inside loss variable, and then we accumulate the loss.item. Specifically, we are accumulating it to the train loss, which is a variable set before the or outside of the loop as 0. So for each batch, we are taking the loss of the model on each batch and adding it to this variable. This variable will contain the accumulated loss after this loop ends. And then, as we said in the trend step, we have to divide the trend loss by the length of DataLoader. Why? This step is considered an adjustment. Adjust metrics to get average loss and accuracy per batch. And now we have to calculate the accuracy by going here. 3. The third step, calculate the accuracy. Let's go test pred labels equals test underscore pred underscore logits dot argmax. Let's get the argmax at dimension equals 1, and then test underscore accuracy equals, let's put a parenthesis, open parenthesis, and then test underscore pred. We have to accumulate it using the plus equals sign. This operator will accumulate the test accuracy. If the test pred labels, or if the test pred logits equals the y, then for each matching element between the test prediction labels here, we have to write test pred labels. If it equals y, then get the sum, and then get the item, divide it by the length of test prediction labels. So this step will calculate the accuracy and accumulate the test accuracy on the test accuracy variable, which is a variable here called testac, initialized as 0 outside of the batch loop, outside of the testing loop. Outside now of the for loop, we have to go outside of the for loop. So notice here the line of the for loop, it's going outside of the loop. We have to adjust metrics to get average, loss, and accuracy per batch by going test loss equals test loss, and then divide it by the length of DataLoader. Test accuracy equals test accuracy and divide it by the length of data loader, and then we have to return back the test loss, comma, test accuracy. Now let's run this function, and congratulations, we have created two functions to train and test our model. Now we will create a simple function that combines the two. So we have to create a third function that combines the two functions. So now let's put here a comment or a markdown, creating a function called train. Let's call it train function. This function to combine train step function, train step, and test step function, test step function. So let's go ahead. We have to import from TQDM library, import tqdm.auto. We have to access the auto module from tqdm.auto, import tqdm, and then let's define train function. This function will take from me a model to train it as torch.nn.module, comma, it will take from me a train data loader, or it receives from me a train data loader, which is as torch.utils.data.dataloader, comma, and also a test data loader. We need to pass in a test data loader to test the model, to evaluate the model, torch.utils.data.dataloader, comma, optimizer. The optimizer is torch.optim.optimizer. We have to put a type hint for the optimizer to be as the optimizer object or the optimizer class, comma, loss fn, the loss function as torch.nn.module, equals by the default equals nn.cross entropy loss. So the loss function by default will be equal to cross entropy loss, and put parentheses to call that loss function. The number of epochs, so how many epochs do we have? As integer, it will be as integer. By default, I will make it 5, as 5 epochs, and then device equals device. So these are all of the parameters that we need to pass in to create the train function. Then we have to create empty dictionary or empty results. Let's call it results dictionary. Results equals a dictionary of train loss. So the loss on the train data, the loss that is computed on the train data will be as an empty list, comma, train accuracy, the accuracy computed on the training data as an empty list. So we have train loss, train accuracy as empty lists, comma, test loss, the testing loss as empty list, comma, test accuracy. Let's also initialize it as an empty list. And then let's create a for loop. So loop through training and testing steps. So the number of epochs for a number of epochs. For each epoch in TQDM, let's use the TQDM library to create a progress bar, then range of epochs. Then we will create two variables. Now the train step, if you recall, the train step function, this function, train step, returns two values. The first value is, it returns two values. It returns the training loss and the training accuracy. So the loss on the train data and the accuracy that is computed on the train data. So we have to create two variables to store these two values, which is in here. We will call them as train loss to store the loss on the training data, and also train accuracy equals, let's call that function, let's call and invoke that function, train step, and pass in model as model, our model, comma, data loader equals train data loader, because we want to train the model on the train data loader. Here in this function train, this function that combines, this function combines train step and test step, both, and calls them together in one hit. So this function takes from me a model to train it and also to test it, and it takes from me a train data loader to train the model on it, and takes from me a test data loader to test the model on it. So here we want to use, you have to be careful, we have to pass in the train data loader, comma, loss function equals the loss function, comma, optimizer equals optimizer, comma, device equals device, and then we have to invoke or call the test step function by going test loss, comma, test accuracy equals test step. Let's call this function test step. This function takes from me a model equals model, comma, data loader as the test data loader. Note here we are using the test data loader, not the train data loader, because when testing we want to test the model on data that the model hasn't seen before, never seen before, comma, loss function equals loss function, comma, optimize or device equals device. And there's an important point here. The test step function doesn't receive an optimizer, because when testing we don't optimize the weights, whereas the function train step, it takes from me an optimizer. Why? Because we need to optimize the weights and the biases inside the model. So the train step function receives an optimizer parameter, while the test step function doesn't receive any optimizer parameter here, because it doesn't need that. It's not necessary. Then we have to print out, here we have to inside this loop for each epoch, so we have to be inside the loop, print, we have to print out the f string epoch, the epoch number as epoch, and then let's go train loss, the train loss as train underscore loss, and let's get the first 4 decimal places by going .4f, then put a pipe train accuracy as train accuracy variable, and then we'll get the first 4 decimal places, put a pipe test loss, so the loss that is computed on the testing data, by going test loss and get the first 4 decimal places, and then put a pipe test accuracy. Let's print this accuracy as test accuracy, and then get the 4 decimal places. After this print statement, let's go ahead and append the items to the dictionary that we have created earlier. So let's now go ahead and update. Let's update the results dictionary by going results, the index or the key train loss, let's append on it the train loss variable, and then results, and then choose the key train accuracy, let's append the train accuracy variable. From where are we getting these variables? These variables from here. This function returns a tuple, and then we are unpacking that tuple into train loss and train accuracy. So we are appending the train loss into the train loss list here. We have here a list, empty list. So we are appending that item into this list of the train loss, also appending the train accuracy value inside this list, train accuracy, and we have to do the same thing for these two, the testing loss and the testing accuracy, by going the same pattern, results test loss dot append the test loss variable. The test loss here we are getting from this function. The test step function retains a tuple, test loss and test accuracy, and then results as test accuracy dot append. We have to append the test accuracy, and as a reminder here, the loss is a measure of how wrong our model is, so how much wrong our model is, while the accuracy is how many right samples per 100 samples the model does get right. So how many samples the model predicts it or classify it successfully or correctly out of 100 samples. And then we have to outside of the loop. Now we are inside the loop. You have to be careful about indentation. All of this code should go inside the loop, and then outside of the for loop here, we want to return the results dictionary, because we want to return this results dictionary that contains the information, contains the performance of the model, both the accuracy and the loss on the training and testing data. So this is a dictionary, and we retain this whole dictionary that is full, and after this for loop, this dictionary will be filled with the data, will be filled with the information about the model's loss and accuracy, both on the training dataset and on the testing dataset. This function train that combines both train step and test step. As you can see here, this function define train, we have called the two functions, train step and test step. So we are performing, this function calls two functions behind the scenes and doing them inside a for loop of 4 epoch for each epoch in TQDM to create a progress bar range of epochs. Epochs is a parameter that we have to pass into here. So how many epochs? By default it will be 5 epochs. So here 5 epochs by default. If you don't specify epochs, it will train the model and evaluate it for 5 epochs. And as we said, the test step function here retains a tuple. So this, when you retain something that is unbounded with parentheses but separated with commas, this is considered a tuple. This is another way to retain a tuple. Okay, so now let's run this function and try it. Optimizer. Yeah, I have misspelled the optimizer here. We can write torch.optimizer. Yeah, we have misspelled the optimizer name. Now we have run the cell successfully. A classic error. Let's try now to train the model. So to train the model, we have to call the train function. So first of all, set random seeds. Let's first set the random seeds by going torch.manual seed as 42, and then torch.cuda.manual seed. We have to set the manual seed as 42. Why? Because we want our experiments to be as reproducible as possible. Then set number of epochs. So how many epochs do you want to train the model for? Let's set a variable as num epochs equals, well, you can set it to whatever you want. You, as a machine learning engineer, you define the hyperparameters. Hyperparameters are external configurations, that you as a machine learning engineer have to define in order to control the behavior of the model. And vice versa, we have parameters. The difference between hyperparameters and parameters: hyperparameters are external configurations, but parameters are internal variables that define the way how the model transforms the inputs into outputs. The coefficients, the weights, the biases are all considered parameters. The parameters are learned from data, while hyperparameters, you define them. They are not learned. They are not inferred from the data. So num epochs equals 5, and then let's recreate an instance of Tiny VGG. So you can recreate it, or you can use the instance that we have used earlier. So let's go model equals Tiny VGG input shape. So the input shape equals here 3. So number of kernel channels, comma, hidden units, let's set it as 10, comma, output shape. The output shape should be length of class names. And remember, we have 4 classes, and we have to move this class instance, this model instance, we have to move it to the device by going to device. Okay, really important step. Now let's set loss function. So set up loss function and optimizer by going loss fn equals, let's use nn. So the loss functions live in the nn module. If you go to torch.nn, this nn module, which we said earlier that it contains the basic building blocks for graphs. Graphs is another word for networks. This module nn, which stands for neural networks. So torch.nn, this package contains loss functions. If you go to loss functions, we have all types of loss functions. We have L1 loss, which is mean absolute error, MAE. We have also MSE loss. We have cross entropy loss. This loss, this criterion, another, always remember, PyTorch prefers to call loss functions as criterion. If you see criterion, this word refers to a loss function. So this criterion computes the cross entropy loss between input logits and target. So we have to use this loss function, which is cross entropy loss. It's useful when training a classification problem with C classes. See, we have C classes. So it's useful when training a classification problem with number C of classes. For example, 3 classes or 4 classes. In our case, we have 4 classes. How can we verify that? By revisiting the class names list, we have 4 classes. So we have to use cross entropy loss. If provided, the optional argument weight should be a 1D tensor assigning weight to each of the classes. So we have a parameter here called weight. If you want to specify a weight, so how much do you want to assign weights to each class? Here we have 4 classes. If you have an imbalanced dataset, for example, if you have 500 images chocolate cake and just 100 cupcakes, 50 macarons, and 30 images sushi, then you have an imbalanced dataset. Then luckily you have a weight parameter which you can use to assign the weight. So you can assign a low weight to the chocolate cake because it has a lot more images, and assign bigger weights to these. But in our case, if you go up, how many images do we have for each class? Here we have 250 images for each class. For the sushi we have 250 images. Also for the cupcakes we have 250 images, training images. Chocolate cake and macarons also have 250. So our dataset is balanced. So we don't have to pass in a weight. Okay? And also you've got label smoothing. Label smoothing is an important hyperparameter that you can set. It's smoothing the labels. And also if you visit how to train state-of-the-art PyTorch models, this is a recent blog post by PyTorch documentation, okay, by PyTorch team. And if you go down here, we have some techniques, okay, that improves the model's results. So you can do some learning rate optimizations, you can do trivial augment, you can do long training, so train for more epochs. You can do you can do also label smoothing. So label smoothing will help the model by this percentage of absolute difference. So will increase our accuracy by 2.9% accuracy. Okay, so this is a technique that you can use and pass it to a loss function such as cross entropy loss, and pass it here label smoothing to optimize the model. In this case, we're not going to use label smoothing. Also, we were not going to use weight because we have balanced dataset. So let's go down. And now let's set up the loss function and optimizer by going optimizer, by going NN. As we said, it lives in the NN module dot cross entropy loss. So we have this loss function of cross entropy loss. And note, we have another type of loss function that's used for classification, which is the BCE loss. BCE loss is binary cross entropy. So this is a cross entropy loss, but is used with binary classes. If you are classifying into 2 classes, for example, macarons and sushi, then you can use BCE loss, or you must use BCE loss. But in our case, we have multi-class classification, so we must use cross entropy loss. Okay, BCE loss again for binary classification. And you can see the algorithm, the equation as here. We have the logarithm of x plus y 1 minus y times the logarithm of 1 minus x, and this criterion creates a criterion that measures the binary cross entropy between the target and the input probabilities. In this case, I'm not going to use BCE loss because we are dealing with multi-class classification, so we are using cross entropy loss. So we are dealing with multi-class classification, And then the optimizer, let's set the optimizer as torch.optim.atom. Let's use the atom optimizer. Atom optimizer will take from me the parameters. So which parameters you want to optimize? I want to optimize our model, this instance, model.parameters. We have to access the parameters. So we have to access the parameters function by calling .parameters, and then we have to adjust the learning rate to be as learning rate equals 0.001. So let's start with the default value 0.001. Okay, let's start with the default value, and then start the timer by going from timeIt. So timeIt is a module in Python which helps us time our model training time. From timeIt import default timer as timer, and then let's go start underscore time equals timer. We have to instantiate or call the function timer, and then parentheses. So now this is the start time, and now let's train the model by calling the function train. So let's train or storing the results dictionary inside the variable called model results equals train. Let's call the train function and then pass in here the model as model, comma, the train data loader equals train data loader, comma, test data loader. Let's pass in it as test data loader, comma, optimizer. The optimizer equals to of the optimizer that we have here, the Atom optimizer. We are using now Atom optimizer, adaptive momentum. And if you want to visit that page, you can go torch optim Atom optimizer, and we have this documentation for Atom optimizer. So Atom optimizer is an algorithm, implements Atom algorithm, and this is the Atom algorithm logic. And if you go down for further details regarding the algorithm, we refer to Atom. This is the paper of Atom optimizer. As you can see here, we have in the archive Atom, a method for stochastic optimization. You can read through that if you want, but now let's go back to our environment and continue coding. Optimizer equals optimizer, comma, the loss function equals loss function. Here the loss function is cross entropy loss, okay? And then we have to epochs equals to num epochs. Num epochs is a variable that I have set before to 5, so num epochs. So feel free to adjust this to train for more epochs. And now let's go ahead and end the timer. Let's end the timer. End the timer and print out how long it took by going end time equals timer, print f string as total training time as the end time minus start time, and then we have to get the first 3 decimal places as seconds. So this line will print how long our model took to train. Now let's run that 3, 2, 1, and hopefully the model will start training. So train the model. Now as you can see, congratulations, we are training our model, and you can see the progress bar, and we are training it for 5 epochs. So let's now read the results. Train loss 1.19, train accuracy 46%, test loss 1.26, test accuracy 40%. I wonder why did we get such results. The train accuracy is 46% and the test accuracy is 40%. The test loss isn't that low, it's so high, 1.2, and also the training loss is 1.1. So if we adjust some of the hyperparameters here, for example, if we train for more epochs, let's try now training the model for more epochs, for 10 epochs, and now let's run that and see whether training the model for longer will help our model learn the patterns. Now let's run that, and I want to stress that now the model is going through the whole architecture. It's now doing convolutions, doing max pooling, and also learning the edges, the corners, the angles from our images. Now you can see the train accuracy now is 49% and the test accuracy is 44%. Okay, so now we have increased the accuracy by some amount of percentages, 49%, and here the test accuracy is 44%. Okay, what about if we changed the learning rate? So you can play around with the learning rate. So let's make it as 0.01. The default value for Adam here is 0.001. Okay, so now we want to make it 0.01. And now let's see the difference. Let's take this here and put it in here to remember what was the last results. Now let's run the model again. Now the model is doing convolution layers, is doing the convolution it's doing the convolution operation, and also it's doing the max pooling, it's adjusting the weights, and also the backpropagation algorithm is updating the weights and the gradient descent and all that stuff. Note that we have train accuracy of 25%, which is way low than before, and we have the test accuracy as 23%. So we can see that adjusting the model's hyperparameters can affect the model's behavior. So just changing the learning rate, look at how many percentages were down or goes down. Train accuracy 25% and test accuracy 23%. So the previous train accuracy was 49%. Now it became 25%. So the difference here is 49 minus 25. The difference is 24 percentages. So when we just changed one hyperparameter, which is learning rate, it went down. It went down from 49 to 25 with a difference of 24 percentages. I want to also to try one experiment, which is that let's go to the train transform or data transform, and let's get rid of this random horizontal flip. So what if we get rid of this transformation, and now let's run our transformation code. If we now go and rerun the datasets again to read the datasets and apply the new transformation, and also go down and rerun the DataLoader cell, we have to rerun the important cells. We don't have to rerun all the cells. Now rerun the DataLoader cell, and also we have to rerun the model again, and we have to go down and rerun the train function, test function, and then and the function that's combining both of them, which is the train function here called train. And now let's run the last cell, which is the cell, and see whether we get an improvements or not. So let's put it as here, and now let's run the model. You can see it's now retraining the model again. Note we are using NVIDIA GPU L4. That's why, because our model is learning too fast, or is training for fast. Now we have train accuracy of 25% and also test accuracy 23%. What if we get the learning rate back to 0.01? So we are now doing experiments on the fly. Okay, run that again. So it's fun to experiment and try different values, try different hyperparameter values, and also adjusting. Always in machine learning you have to experiment with the model. So now we've got train accuracy of 49% and the test accuracy as 44%. So there are ways to improve the model, which is, for example, you can also train the model for longer, for 20 epochs. You could also feel free to try changing the, for example, the number of hidden units. So let's try this experiment. Let's try to increase the number of hidden units from 10 to, for example, 32 hidden units. But now you have to keep in mind that result, which is train accuracy 49%, and this, and now let's run again. Now we are we are training the model again. So we have, so now we've got improvements. Now we have 50% accuracy. Now it's going up 55%, 59%. So just by increasing the number of hidden units, which is this, if you go to CNN Explainer website, here we have 10 hidden units. Okay, 1 2 3 4 5 6 7 8 9 10. We have increased it from 10 to 32, and it increased the accuracy, the train accuracy, to 59%. So just by changing the number of filters or the number of kernels, we have increased the accuracy of our model. Now let's try. That's enough experimenting. Let's go ahead and try to plot the loss curves of our model. You can always feel free to change the hyperparameters, to play around with the model's transformations and try other transformations, like try rotating the images, rotating the images and see what the model performs, or what the model performance is going to be look like. And also try different hyperparameters, like for example, you can play around with the stride value here. If you go here, you can play around with the stride value. You can increase it or decrease it, or kernel size, padding, shrink the padding, and also you can do a lot of experiments. Now let's go define plot loss curves. Plot loss curves. Pass in here the results as a dictionary of string, comma, list of float. So the dictionary will be a string. The keys will be as strings, because now we have model results dictionary. This is a dictionary containing all of the results of our model. So we have 10 epochs. That's why we have 10 train losses, and we have 10 train accuracies, and also we have 10 test accuracy, 10 test losses, and also 10 test accuracies. Let's try and plot these values. So this is a dictionary. The keys are of type strings, and the values are of type list of floats. Now let's go ahead and put a docstring plots training curves and or of a results dictionary, and then get the loss values of the results dictionary, training and test. So let's go ahead and loss equals results. Let's access the results, the model results dictionary, which is in this case we pass it into here, so we call it results at index train loss. Also we want to access the test loss by going results and then access the test underscore loss key. The second step is get the accuracy values of the results dictionary, and then training. Let's go training and test. Accuracy equals results, and then access the train accuracy key. Also the test accuracy equals the results dictionary, and then access the test accuracy key. Here we have results. We have to write results in the right way. Oh, we have a misspelling here, results. So that's why we were getting yellow lines. We have to adjust this to results. So we have our results at index train accuracy and results at index test loss. We have to access here the train accuracy and the test accuracy, and here we access the training loss and test loss. Let's set up a plot using PLT, the Matplotlib library, by going plt.figure. Fig size equals 15,7. Let's make it a big figure, 15,7. And also we have to figure out here, before this step, we have to figure out how many epochs there were by using the epochs equals range, the function range, and then pass in length of results, and then access the train underscore loss key. So by accessing the train loss key and then getting the length of that, passing it to our range function, we get the number of epochs for how many epochs we trained our model. Plot the loss, plt.subplot. Let's create a subplot. Let's create a subplot of 1 row, 2 columns, and then let's access the first subplot. The first subplot will contain a plt.plot. Let's plot the epochs on the x-axis, and on the y-axis let's plot the loss. So the train loss here, we have the loss is a variable that equals results, and then access the train loss, comma label, let's label it as train loss. Then plt.plot epochs on the x-axis, comma test labels, test loss, comma label equals test underscore loss. And now let's set the title as loss. So the loss curves, the curves of the loss, plt.xlabel as epochs. plt.legend, let's show a legend. And then the second step is plot the accuracy. By going plt.subplot, let's construct a subplot of 1 row, 2 columns, the second image, and then plt.plot. Let's plot a line of epochs on the x-axis, and then on the y-axis we have accuracy, comma label equals train accuracy. Then plt.plot, let's plot the epochs on the x-axis, the test accuracy on the y-axis, and label should equal to the test accuracy. Then we have to go plt.title, set the title as accuracy %, and then plt.xlabel as epochs, and then let's set the legend to be enabled to show a legend. Now we have a fully working function that will plot our loss curves and training loss curves. Let's go plot loss curves and pass in the model results. 3, 2, 1. Now we are about to see a wonderful figure that shows the loss curves of the model. So 3, 2, 1, run that, and yes, now we have plotted our loss curves and training accuracy curves. So there are good news. The good news is that the training loss is going down, which is the perfect loss curve. So if you search here in Google loss curves, and if you go to here images, so the best loss curve is the loss curve that goes down. So we want, so the ideal loss curve, if you go to here to Google's guide, and the ideal loss curve is this curve. So this is considered the ideal loss curve. So machine learning would be, if you read here, machine learning would be much simpler if all your loss curves looked like this the first time you trained your model. So if you train your model for the first time and you get a loss curve like this, then congratulations, that's considered a perfect model. The loss is going down over time. So over the steps is another word for epochs. So over epochs, over time, the model learns generalizable patterns, and the model is able to learn perfect patterns, perfect features, and then the loss goes down. So we want the loss to reduce. We want to decrease the loss over time. Here, the training loss is going down over time. So we have here epoch 1, 2, 3. So over time, the loss is going down. But the test loss here, you can see it's going down, then goes down, 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 then it goes up again, then it goes down, then up, up, up. So this means that our model is overfitting, because the model is performing really well on the training data, but the testing data or the testing loss went up. So it was going down for a certain number of epochs, but then it went up. So the model from here started to overfit. So from this point, from epoch 3, so this is epoch 3, because we are starting counting from 0. So from epoch 3 the model started to overfit. How to solve overfitting? Well, to solve overfitting, there are some possible solutions. You can reduce the complexity of the model. So maybe the model is too complex here. If you go back to the architecture, so maybe the architecture is too complex. You can reduce it. For example, get rid of this convolution block 2 and see how it performs without the convolution block 2, the second conv block, because the more layers, the more complex the model, and then the more chance that the model will overfit. Okay, and also you can try to train for less epochs. Okay, for the testing loss here, for the testing accuracy, for the accuracy, for the train accuracy is going up. As you can see, the train accuracy is going up. It's increasing, so the accuracy is going higher, which is a good thing, a perfect thing, really important thing. The accuracy goes up, very nice. But the testing accuracy, it was going up, but at some point it went down, so the model started to overfit. So I will let you explore more on that to try and solve this problem, why our model is overfitting. But in this lecture, we focused on building the Tiny VGG model from scratch. We also learned how to prepare the custom datasets, because we have read our images from here using the classes like ImageFolder. We have used the class ImageFolder to read our images, to select images, or to grab images from inside folders, which is a really important skill for any machine learning engineer. And also we learned how to transform images and visualize the transformed images. As you can see, we visualized the transformations happening to different images. And also we learned how to convert those datasets into DataLoaders. Here, if you can see, we have DataLoaders, how to turn your datasets into efficient DataLoaders and set the batch size as 32. This is another hyperparameter that you can play around and test. See if we make the batch size 1, for example, is the model going to get better or not? We can try that. For example, if you want to try this experiment, we can do that easily. Let's go down now and retrain our model and see whether this will improve the model as an experiment. We can take the last line here and put it into here. Let's retrain our model and see whether it will perform worse or better. So we started with accuracy 24%, and now the train accuracy is 24%, 23%. So I think this experiment would not bypass the last experiment, because we are, after each image, the model is updating its weights. So after seeing each image, the model will update its weights and its patterns, as you can see. Whereas before we had batches of 32 images, and the model updates its weights after each single batch, after 32 images. And now we end up with train accuracy of 24% and test accuracy as 25%. And if you visualize the loss curves, they will change. Here we can visualize them again using our function, and you can see that now we have very bad loss curves. So this is the end of the lecture. I hope you learned something new. We have explained several concepts about convolutions, how to visualize your architecture using torchinfo, and a whole different tasks were done in this project. So I hope this was a interesting course. I was excited to create it, and I hope I meet you in next courses. So thanks for watching, and see you in new tutorials.